वर्षा, आपकी आवाज नहीं आ रही है। डॉक्टर वर्षा, आपकी आवाज नहीं आ रही है बिल्कुल। चल रहा है। चल। मीटिंग आईडी बोलो।
सब टेस्टेड था मैम।
ऐसा हो सकता है कि अपन स्टार्ट कर दे, फिर इसको
ठीक है।
रिकॉर्डिंग को यूट्यूब पे अपन बाद में
यूट्यूब लाइव कर दिस मीटिंग इज बीइंग लाइव। मैम लाइव स्ट्रीमिंग बंद कर देते हैं, बाद में रिकॉर्डिंग एक बार लाइव स्ट्रीमिंग बंद करी तो कॉन्फ़िगरेशन वापस नहीं चलेगी। हाँ
तो देखो बाद में इसको देखो।
मैम क्या आपको अब सुनाई दे रहा है? अब इसका स्पीकर, हाँ उनको सुनाई दे रहा है, मुझे दिख गया उनका। हाँ ना, अब उनकी आवाज
क्या बोल रही मैडम, बोल भी रही है?
मैम एक बार अनम्यूट करके बोलिएगा।
हाँ दे रहा है।
वो तो दे रहा है, पर अपन को नहीं दे रहा। चलो ठीक है, आप शुरू करो, तब तक समझ।
है?
I'm sorry for the delay and technical glitch. Let's resume the session. I once again welcome our eminent dignitaries from various fields of science. Our most important guest, chief guest is Dr. Vivek Katare, sir. And our speakers are Dr. Anita Dutt Kunar, ma'am, Mr. Vikesh Chauhan, Mr. Praveen Srivastava also represents Anton Par. What makes this gathering especially meaningful is the breadth of expertise in the room. Government representatives, academic leaders, and industry professionals all have come together not only to share knowledge, but also to spark collaboration. Our chairman, Shri Jambu Bhandari ji, was supposed to join us online, but due to some urgent work, he is not able to join us. So, but his leadership skills are always with us. Though joining us virtually, our director, Dr. Pratibha Singh's presence is as impactful as ever. Ma'am, your commitment to excellence makes every initiative shine brighter. With profound respect, I welcome the guiding light, our principal, Dr. Archana Srivastava, ma'am, Vice Principal, Dr. Renu Mishra, ma'am, Law Principal, Dr. Anju Vajpayee, and our esteemed faculty members. To our research scholars and students, we welcome you with great pride. Workshops like this find their true purpose in your enthusiastic participation. To begin this auspicious occasion with positive energy, let us invoke the blessings of Almighty through Saraswati Vandana. May I request Dr. Neena Arora Madam to kindly accompany our guest for offering flowers to Goddess Saraswati. Okay. एक बार सर आ जाए वैष्णव अभी एक बार सर आ जाए उसके बाद स्टार्ट करें
या बुद्धे तु तुषार हार धवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्कर प्रभृतिभिः देवे सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसार परमा आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीं भयदा जाड्यान्धकारापहा हस्ते स्फटिकमालिका विदधतीं वासरे संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदां बुद्धिप्रदां शारदां बुद्धिप्रदां शारदां
Thank you, Madhvi and Krishna. May the vibrations of these sacred words guide us towards wisdom and innovation. I request the dignitaries to please be seated on the dais. A sapling is the most beautiful way to welcome someone. Today, as we honor our guest with green saplings, we reaffirm our commitment to green chemistry and sustainable living. I request our principal, Dr. Archana Srivastava ma'am, to present a sapling to our chief guest, Dr. Vivek Katare sir, as a mark of our gratitude. I now request our convener, Dr. Neena Arora ma'am, to welcome our guest speaker, Dr. Anita Dutt Kunar ma'am, with a sapling. I invite Dr. Kiran Chandelier, Associate Professor Chemistry, to present a sapling to Mr. Vikesh Chauhan, Representative Anton Bar. I request Ms. Supriya Singh, Assistant Professor Chemistry, to welcome Shri Praveen Srivastav ji with a sapling. Thank you. Now, to formally set the tone of today's workshop, I invite our principal, Dr. Archana Srivastava ma'am, to deliver the welcome address.
Om Shri Sai Ram. My humble pranam at the lotus feet of Shri Sathya Sai Baba. I'm beginning with a beautiful verse about education. The beautiful thing about learning is that no one can take it away from you. Good morning, everyone. Respected Chief Guest, esteemed resource persons, dear colleagues, and my beloved students. On behalf of Sri Sathya Sai College for Women, Bhopal, it is my proud privilege to welcome you all to this one-day national workshop on unlocking the power of Monowave Reactor, organized by the Department of Chemistry under the aegis of IQAC. We are deeply honored to have with us our chief guest, Dr. Vivek Katare Sir, Executive Director of MPCST Bhopal. Sir, your gracious presence adds immense value to this program, and we are eager to hear your words of encouragement and wisdom. I also extend a warm welcome to our esteemed resource person, Dr. Anita Dutt Konar, UGC Assistant Professor, RGPV Bhopal, and Dr. Vikesh Chauhan, Regional Sales Manager North, Antonpar, Delhi. Your expertise and insight will truly enrich this academic journey for all our participants. At Sri Sathya Sai College for Women, we firmly believe in the power of education as a tool for empowerment, transformation, and progress. Our mission has always been to nurture confident, capable, and creative women who can contribute meaningfully to the society. Today's workshop is not merely an academic exercise, it is a step towards building that nation by encouraging scientific curiosity, hands on learning, and innovative thinking. The focus on the Monowave Microwave Reactor reflects the growing importance of modern research methodologies and their applications in shaping the future of science. It is heartening to see our students and scholars step into this world of new opportunities, equipped not only with knowledge but also with confidence. I take this moment to sincerely thank our chief patron, Shri Jambu Bhandari ji, chairman of the college governing body, and our respected director, Dr. Pratibha Singh Madam, for their unwavering support and guidance. I also deeply appreciate the tireless efforts of our convener, Dr. Neena Arora, our co-convener, Dr. Varsha Saxena, and the organizing secretaries, Dr. Kiran Shandile and Mrs. Supriya Singh, along with the entire organizing committee for bringing this workshop to life. And now, to my dear students, this platform has been created for you and only for you. Make the most of it. Ask questions boldly. Seek answers tirelessly. And let your curiosity lead you beyond the boundaries. Remember, when women learn, society rises. When women innovate, the future transforms. Together, let us make today not just a workshop, but a celebration of knowledge, empowerment, and discovery. It is rightly said, science knows no country because knowledge belongs to humanity and is the torch which illuminates the world. With these words, I once again welcome you all and wish this workshop a great success. Thank you. Sayonara.
Thank you, ma'am. Now, to open the theme of this one-day workshop and share the vision behind this event, may I call upon our enthusiastic convener, Dr. Neena Arora.
Thank you, Dr. Varsha. Sairam, good morning to all, respected dignitaries on the dais, Honorable Chief Guest, Dr. Vivek Katare ji, Executive Director, MP Council of Science and Technology, Director Dr. Pratibha Singh ji, our resource person, respected Dr. Anita Dutt Konar ji, UGC Assistant Professor Rajiv Gandhi, Pradhyogiki Vishwavidyalay Bhopal, and Shri Vikesh Chauhan ji, Regional Sales Manager, North, Anton Par, New Delhi, Principal Dr. Archana Srivastav ji, Dr. Anju Bajpai ji, Principal Law College, Vice Principal Dr. Renu Mishra ji, distinguished faculty members, eminent researcher, dear students, and all the participants who have joined us online. It gives me an immense pleasure to welcome you all in the inaugural session of National Workshop on Unlock the Potential of the Monowave Microwave Reactor. Chemistry built the modern world from material to medicine, from energy to industry. We live in an age where science and technology are being called upon not only to advance knowledge, but also to respond to the urgent challenges of development, climate change, and sustainability. Chemistry, as the central science, has a unique responsibility in this regard. The way we design molecules, conduct reactions, and scale up processes has far reaching consequences for human health, for the environment, and for our future. It is here that green chemistry becomes a guiding light. Green chemistry is not just a set of principles, it is a philosophy of innovation to design processes that minimize waste, reduce energy use, and employ safer, renewable materials. As Paul Anastas, often called the father of green chemistry, rightly said, the great challenges of our time is not to choose between environment protection and economic development. It is to achieve both. The monowave microwave reactor exemplifies this philosophy beautifully. Unlike traditional methods of chemical synthesis, which often demand long hours, large amount of energy, and hazardous solvents, microwave-assisted synthesis offers speed, efficiency, and sustainability. Reactions that once took hours or days are now completed in mere minutes. Higher yields and greater purity reduce the need for repetitive trials. Reduced solvent use, reduced energy demand, and less waste generation makes it eco-friendly. Allow me to share a personal journey. My exposure to microwave-assisted synthesis and association with the green chemistry began in 2005 when I attended the International Conference on Green Chemistry organized by the Green Chemistry Institute of American Chemical Society in Washington, D.C. I was amazed to see how microwave were revolutionizing chemical synthesis. Again, in 2007, my paper was accepted for the presentation in the same conference. I again attended and discussed with senior professors working in this field. At that time, purchasing a dedicated reactor seemed impossible due to its high cost, and also, if I searched, I didn't find any reliable microwave reactor. My search remained continued. And then, with the support of FIST grant of DST, we were finally able to acquire a monowave microwave reactor in 2016. Then we did few work and happy to share. Then three faculty members, me, Dr. Kiran Shandil, and Dr. Varsha Saxena of the department, attended Green Chemistry Conference of International Union of Pure and Applied Chemistry, IUPAC, in 2018 in Bangkok. Microwave synthesis is in PG on few reactions like Beckmann rearrangement, aldol condensation, Mannich reactions. We successfully synthesized oximes from a reaction that conventionally required prolonged heating. Using the microwave, it was completed in just 4 to 5 minutes with excellent purity. We synthesized metal nanoparticles, a process usually considered tedious, and time consuming. With microwave synthesis, we achieved it in minutes without excessive chemical or waste. We also synthesized chalcone by aldol condensation, which are important intermediate for synthesizing heterocyclic compound with various pharmacological activities like antiviral, anti-cancer, and anti-inflammatory properties. We have synthesized fluorescein dye, which is used in variety of diagnostic and surgical procedures. These are few examples which we have done and found very good results. You will see the product and demonstration also. This workshop has been designed with all of you in mind. Today, you will not just hear about microwave synthesis, you will also experience and at first hand and witness the power of microwaves in reducing time, cost, and environmental impact. Climate change, pollution, and resource depletion are realities we can no longer ignore. Laboratories, though hubs of discoveries, also leave a footprint. Stockholm Declaration in May 2025 on Chemistry for the Future emphasized that our teachers, students, and practitioners of chemistry need to be trained now, ensuring that the invention of new chemicals or chemical transformation integrate health, sustainability, and inherent safety as essential element of performance. Keeping this in mind, we organized this workshop to sensitize, to create awareness about the urgent need for greener and safer chemical practices to save our Mother Earth. The chemistry of today must safeguard the environment of tomorrow. To conclude, I urge all participants to approach this workshop with curiosity, creativity, and responsibility. Let this not be just a training program, but a stepping stone towards building a greener scientific future. Together, let us unlock not just the potential of the monowave microwave, but also the potential within ourselves to innovate responsibly for science and society. Chemistry once reinvented the world. It is time to do it again with fresh insight, new tools, and sharper sense of purpose. We can, we must, and we will. Yes, we will create a sustainable future. Thank you so much, Sathya.
Thank you so much, Neena ma'am. I'm sure the participants must be feeling a little more curious about the workshop now. Now, with utmost respect, I invite our esteemed director, Dr. Pratibha Singh Madam, to address this gathering. Ma'am, your words are always a source of guidance, and we eagerly await your thoughts to set the tone for today's deliberations.
कुछ बोले थे मैडम की नहीं आ रही मैडम की आ रही मैडम की नहीं आ रही
हेलो, मेरी आवाज आ रही है वर्षा?
आ रही है
मैम आ रही है।
Okay, now I continue. We have excellent facilities for students, a big library, science labs, computer labs, sports ground, gymnasium, and girls' hostel in the campus with beautiful gardens. We are regularly organizing seminars, workshops, training programs, spiritual camps for students to help them expand their knowledge and skills. In today's context, sustainability is a necessity of our time. When we look around, the challenges are clear: climate change, resource depletion, plastic pollution, and toxic emissions. The way we have produced, consumed, and discarded chemicals in the past century has given us growth, yes, but also a heavy ecological burden. Sustainability means meeting the needs of the present without compromising the ability of future generations to meet theirs. As Albert Einstein wisely said, we cannot solve our problems with the same thinking we used when we created them. Green chemistry is that new thinking. Green chemistry is not just about protecting the environment, it is also about economic sustainability. Clearness process reduce cost of waste treatment, improve efficiency, and create new business opportunities in the following field of green technology. Green synthesis used these principles into practice. Microwave assisted synthesis cuts reaction times from hours to minutes, saving energy. Biodegradable polymers replace plastics that choke our oceans. Eco-friendly pharmaceuticals reduce harmful byproducts in drug manufacture. In every case, we see that green synthesis is not just cleaner science, it is smarter science. Sustainability is not the task of scientists alone. It requires industries, policymakers, educators, and communities to adopt and support greener practices. As we look ahead, we must remember sustainability is not a choice but a necessity. Every decision we make in laboratories, industries, and classrooms must align with the vision of greener, safer, and more sustainable world. Green chemistry and green synthesis provide us with the scientific and ethical roadmap to get there. Let us remember the greatest innovation of our century will not be a single invention, but our ability to assign human progress with the law of nature. As Mahatma Gandhi once said, the world has enough for everyone need, but not enough for everyone's greed. Green chemistry gives us the tools of honor that wisdom by ensuring that progress and preservation walk hand in hand. Let us pledge today to practice, promote, and pass on green chemistry, not just as a science, but as a commitment to sustainability and to life itself. The famous African proverb reminds us we do not inherit the earth from our ancestors, we borrow it from our children. That thought alone should make us rethink every chemical we design, every process we run, and every product we consume. I believe that this national workshop will be very beneficial for participants, research scholars, and our students. I extend my heartfelt thanks to all the distinguished speakers, dignitaries who have kindly agreed to share their expertise with us, and congratulate Dr. Neena Arora, head of the Department of the Chemistry, and all faculty members of chemistry for conceptualizing and executing this program with such academic vision and commitment. Thank you all and best wishes.
Thank you. Thank you so much, ma'am. Your thoughts certainly set the tone for this workshop. As the proverb goes, a leader is one who knows the way, goes the way, and shows the way. It's an honor to have with us our chief guest, Dr. Vivek Katare, Executive Director, MPCST Bhopal. Dr. Katare has not only contributed immensely to the academic world, but has also served as a guiding light for young researchers. I will now read a brief biodata highlighting the remarkable achievements and contributions in science and technology. Sir completed his PhD in the year 2000 from MS University, Baroda. He has approximately 25 years of administrative and research experience in MPCST. He has served as head, land use and urban survey division. He has been in charge of many committees, successfully completed many research projects in the field of land use planning and wasteland updation. Sir has supervised 6 PhD students and has many publications of international repute to his credit. Sir has been the recipient of many awards, some of which include Outstanding Contribution Recognition by the Director General of MapCost for NRIS project, Technical Expert nominated by MOUA for Amrit, and National Geospatial State Award in 2012. It's my proud privilege to invite our chief guest, Dr. Vivek Katareji, to deliver his address.
Thank you. The dignitaries sitting on the dais, Dr. Pratibha Singh, Director, Sathya Sai College, Chairman, Mr. Jammu Bhattari, who is the Chairman of the college governing body, Dr. Archana Dikshit, convener of this, Dr. Archana Dikshit, Principal, Sathya Sai College, Dr. Neena Arora, Head, Department of Chemistry, and convener of this workshop, Dr. Anju Bajpayee, Dr. Renu Vajpayee, Dr. Anita Datta Karnal, who is the UGC fellow, and Mr. Vikesh Chauhanji, who is the person for the nanowave microwave reactor for this zone. It is one kind of a odd situation, like a person like me, when this invitation was come to me through Madam Neena Arora, because chemistry for me, it is just when I studied in my matriculation days, late in 80s, and after that, I'm never so correlated with chemistries and all these basic sciences. And my area of expertise later on changed to somewhere around planning. And from last 38 years, I'm working for the planning of the state of Madhya Pradesh. By my present position, basically, I'm an administrator, but by my own expertise, I'm a scientist. So, a person from our era who born in 60s or maybe late 50s or 55, they have seen the transformation. Because most of you born after 90s or maybe late 80s, but transformation in terms of scientific advancement, transformation in terms of our own daily lifestyles, everything is quite clear. So, in each road where you are traveling has been planned by us. Each area where you are residing has been planned by us. On this planning, earlier in late 70s, it has been done through various kinds of survey methods, traditional surveying methods. But now this entire surveying has been shifted to the satellite remote sensing, drone remote sensing. Then we have aerial remote sensing, aerial platforms. So you see the advantages and advancement which taken place after 80s, when first satellite was launched in 1982, Aryabhatta. And later on, these developments were taken place by increasing the resolution of the satellites, their repeated coverage to monitor the areas, and sensors who can even predict the smallest object of the Earth. And nowadays, most of our geostationary satellites been targeted to the northeastern border, which is China and Nepal, and the western border with Pakistan. So they are continuously monitoring the and any kind of activities which is taken place in these areas. These satellites having even the night-borne capabilities, even thermal remote sensing. And when we are talking about, when this invitation was came to me, it is something around about microwave. So microwave we are using in our areas, particularly for flood inundation mapping, because any kind of a active energy cannot be penetrated by the clouds. So microwave can penetrate the cloud and resource and gather the earth information, which is one of the major scientific advancement in assessment of floods during rainy season in the entire country. Department of Space is doing all these things for their respective states, but MP Remote Sensing Application Center, which is under MP Council of Science and Technology, also using microwave remote sensing for flood and inundation mapping. Now, as far as this workshop is concerned, which is quite interesting, when we see the different kinds of developments in various areas, particularly in the field of chemistry. Now, chemistry is the science of basically father of the science, because it has been used in across any arena of the science, whether you assume for the medical sciences, whether you think about the agriculture sciences, whether you go for the pharmaceutical industries, whether you go for the chemical industries, whether you go for the textile industries, everywhere the chemistry has its own importance. So now the policies are turned about after 70s. We never thought of a term pollution, or nor this term pollution was I have anywhere listened during 70s or before 70s. But then comes the pollution. Why pollution? So this thought came into existence in 1970s when the Environmental Protection Agency, USA, has started thinking on the environmental pollutions and all those parameters. Then gradually, after industrialization and after changing the total scenario of the world across the world, and the uses of various chemical parameters and various other actions, we thought about that some legislation should be introduced to control these kinds of pollutions, whether it is from the fossil industries, whether it is from the textile industries, whether it is from the fuel, oil, natural gas, and coal. But in today's context, why we are talking about green? We are talking about green not only in the chemistry, but we are talking about green buildings. We are talking about blue plants, which is normally related to the conservation of the water bodies and our reservoirs, to avoid all kinds of pollutions in these reservoirs. And now we are talking about green chemistry. So this term, basically green chemistry, was first came into existence in 1990s. And Paul Anastas, who is the father of the green chemistry, introduces this term, green chemistry. Now, the green chemistry basically is slightly different with the environmental chemistry, where environmental chemistry, we cannot correlate both of them, environmental chemistry and green chemistry, because environmental chemistry is other thing and green chemistry is other thing, which avoid the pollution, even not allow any kind of a pollution. And that is the basic of green chemistry. While in environmental chemistry, there is a chances of any kind of pollutant material may be inducted, even in spite of all kinds of guidelines and regulations. Now, coming to the basic core of this workshop, since lots of students are sitting over here, in last 30 years or more than 30 years, because we are continuous monitoring that the interest of students in the faculty of science is reducing by an alarming rate. Most of the students after 70s very least interested to join the science. Madhya Pradesh Council of Science and Technology started one mission, which is a mission mode program, that we select 320 students from 10th, 11th, and 12th class who are meritorious students and send them to various laboratories, national level laboratories, whether it is DRDO, whether it is Department of Space, whether it is plant, nuclear, and nuclear power station also, to understand what the science, what are the developments are taking place in these institutions, and what is the roadmap of future research in science and technology. So these 325 students, we select 100 students for scholarships. They have to go for examination before selection. But after induction of this program, I have assessed the impact assessments of turnover of students from Madhya Pradesh towards science. But it is very marginally increased by 0.15% in last, I mean, after 2008, because 2008 means after 17 years or so. So why these things are happening? Because out of every 100 students, 80 used to select their career in arts, commerce, and engineering. So you left with 20 students who opt for the science faculty. And students are much more oriented towards job. So after graduation or post-graduation, they go for the business, MBA, and other business courses and try to get the jobs. Now, these are some of the some problems are related to our economy. Some problems are related because we don't have that kind of a job where we can provide it. Although the scenario is quite different because we have more than 1.45 CR jobs vacant still in the government sector. But because of the government policy, we are facing crisis. Our students are facing crisis. So we have to see the new areas where we can, but we cannot neglect the science. Science also have a very, very charming career advancement. Now you see the Chandrayaan, the landing of Vikram rover on the South Pole. It is a scientific achievement. India is the first country who stepped on the South Pole of the moon. So there are scientists. One time when this privatization was taken place, most of the senior scientists from ISRO left ISRO. At that time, the salaries structure was very low. So they have opted for the private sector. But there are challenges, there are options, there are very, very advantageous careers in various sectors of science, whether it is pharmaceutical sector, whether it is textile sector, whether it is space sector, whether it is defense sector. So it's my humble request to all students who are studying in science that be positive to make a career in your subject where you can take this country across any of the country of the world. Whether it's because you see in US also what maximum brain is transported from India. China has different kind of a policy, but India don't have that kind of a rigid policy where a student after studying in US should come to India and work for the country. China has that kind of a policy that they study abroad, they should come and they have to participate in the country's economy. So, by and large, it's my best wishes for this workshop on Monowave Microwave Reactor, particularly which is based on microwave radiation synthesis. And I hope that this is one of the advanced instruments. And maybe I think I have a discussion with the principal that this is the only instrument in our city. So it is request from my side and also from this side of college faculty that use of this kinds of facilities is opportunity to all of researchers, even faculties, to produce something extraordinary, not for the college, for the state, and for the nation also. Thank you very much.
Thank you so much, sir, for those illuminating words. Your inspiring journey and valuable insights will surely enlighten us all. As a token of our gratitude and deep respect, I will now respect Principal Dr. Archana Srivastava ma'am to present a small memento to our chief guest, Sri Vivek Katare, sir. May this serve as a remembrance of today's meaningful association. Thank you, ma'am. I now request Dr. Kiran Chandelier, Associate Professor Chemistry, to propose a formal vote of thanks.
धन्यवाद वर्षा। महाविद्यालय में आयोजित नेशनल वर्कशॉप ऑन अनलॉकिंग द पावर ऑफ मोनोवेव माइक्रोवेव रिएक्टर के मुख्य अतिथि आदरणीय डॉक्टर विवेक कटारे सर, एग्जीक्यूटिव डायरेक्टर मध्य प्रदेश विज्ञान एवं प्रौद्योगिकी परिषद भोपाल का इस कार्यक्रम में अपना अमूल्य समय देने के लिए महाविद्यालय परिवार की ओर से मैं हृदय से आभार व्यक्त करती हूँ। आपके प्रेरणादायक एवं ज्ञानवर्धक शब्दों ने हम सभी को प्रेरित किया है। आपकी उपस्थिति ने हम सभी को गौरवान्वित किया है। धन्यवाद सर। मैं डॉक्टर अनीता दत्त कोटनार, यूजीसी असिस्टेंट प्रोफेसर, राजीव गांधी प्रौद्योगिकी विश्वविद्यालय, श्री विकेश चौहान सर, रीजनल मैनेजर नॉर्थ एंटन पार्क न्यू दिल्ली, एवं उनके सहयोगी श्री प्रवीण श्रीवास्तव जी, रीजनल मैनेजर एंटन पार्क का हृदय से धन्यवाद ज्ञापित करती हूँ। आप सभी का सहयोग एवं समर्थन हमें हमेशा मिलता रहा है। आप सभी ने इस कार्यक्रम की गरिमा बढ़ाई है। मैं हमारी डायरेक्टर मैडम डॉक्टर प्रतिभा सिंह का विशेष धन्यवाद करती हूँ, जिनके मार्गदर्शन, नेतृत्व एवं प्रेरणा से यह कार्यक्रम आयोजित हो पाया है। मैडम ने ऑनलाइन जुड़कर हमारा मनोबल बढ़ाया है। हमारे कॉलेज की ऊर्जावान प्रिंसिपल का सहयोग हमेशा प्रेरणादायक रहा है। मैं उनका हार्दिक धन्यवाद करती हूँ। धन्यवाद मैडम। हमारे इस कार्यक्रम में शामिल श्री सत्य साई लॉ कॉलेज की प्रिंसिपल डॉक्टर अंजू वाजपेयी मैडम का मैं हार्दिक धन्यवाद करती हूँ। आपकी उपस्थिति से हमें संबल मिलता है। मैं वाइस प्रिंसिपल डॉक्टर रेणु मिश्रा मैडम का बहुत बहुत धन्यवाद करती हूँ। आपका सकारात्मक दृष्टिकोण हमें प्रोत्साहित करता है। मैं ऑनलाइन और ऑफलाइन पार्टिसिपेंट्स का हार्दिक धन्यवाद करती हूँ। आप सभी हमारे साथ इस राष्ट्रीय कार्यशाला में उपस्थित रहेंगे। सभागार में उपस्थित मेरी साथी प्राध्यापिकाएं, आईटी सेल के सदस्य एवं हमारे प्यारे विद्यार्थियों का मैं हृदय से धन्यवाद करती हूँ एवं इसी तरह सहयोग की अपेक्षा करती हूँ। अंत में मैं उन सभी का बहुत बहुत धन्यवाद करती हूँ जिनकी भागीदारी प्रत्यक्ष एवं अप्रत्यक्ष रूप से रही है। धन्यवाद, शुक्रिया, सबका आभार।
Thank you, Kiran ma'am. Dear participants, with this, we conclude this session and we proceed to FIS Lab for formal inauguration of this workshop. After that, we'll have a short tea break and then we'll assemble back here for technical session 1.
चार्जर कहाँ है इसके पास? नहीं है, पूछ रही। हाँ मैं दिया था उसको। दिया है मैंने, उसको ही दिया है पुराने वाले को। फिर से लेके आती हूँ। बोल भी आशा मैडम ने हाथ में जो दिया था ना वही इसका चार्जर है। हाँ ना, नहीं, वो खाली है ना वो पोर्ट। वो लग सकता है पता लगाऊं। नोट करो।
बाइक कहाँ है यहाँ पे? दो, सर को दो। Yes, sir. Yeah, right.
Acha, okay.
Yes, sir.
So this is the microwave reactor, sir. So basically, you can perform all kind of services in this reactor. You are for organic synthesis, organic synthesis, polymer, nanomaterial. You can perform functions. You basically open yourself, one kind of things where for sensitive, onions or the heating here. So this is the thing that is the conventional. This is using the microwave reactor. So here the difference is the heating rate is very fast, right? So the reaction is simple, like 1 hour, 2 hours, 4 hours, 6 hours. Some reaction takes 2 to 3 days to complete. But in general, in this microwave reactor, closed vessels. So what is the difference between domestic microwave and yeah, so that's what I'm saying. Domestic microwave is basically just a short so here the heating temperature is controlled. Right? So right. So it has all the kind of sensors, safety protections, reaction, mixture, reaction. All this and put it inside the microwave. You do the programming install. You set so there is a basically a kind of safe. The water has a boiling point of 100 degrees. You can put your whatever set temperature food, put it in the 1000 degree oven, it will be 100 degrees. It will boil and it will come. Like this, if you can you know, the water will take more than 20 or 16, 300 degrees. But it depends. Because there is a boiling temperature of the water, right? So that's the 360. So the instrument should be able to handle that. So this instrument is designed for 20 bars pressure. Right? So you can any reaction at the temperature with the pressure inside the vessel is up to 20. So you can go up to into 60 degrees Celsius.
हाँ जी सर, ये नंबर का ये छोटे जिंक का, जिंक ऑक्साइड का और कॉपर के और सिल्वर के हमने बनाए थे। this fluorescent light का मैंने बताया था, इसको हम यदि वाटर में डालेंगे तो फुल एकदम से चल जाएगा, जो यूज होता है इंटरेस्ट एज अ बिजनेस है। ये जो कॉन्सेप्ट का है, this is सही है, वो भी बनाने को फर्स्ट जब बैंकॉक में जो बैंकॉक में प्रेजेंट किया था तब वो मुझसे करने आए थे। अभी जो मेरी बच्ची ने थीसिस का है हाँ, तो वो उसका जिंक ऑक्साइड सर इसका बहुत सारी यूटिलाइजेशन है। तो जैसे मैंने भी इसके बताया था कि ये जो फ्लोरोसेंट आई है वो इसमें और जो जर्नल्स हैं वो भी फार्मास्यूटिकल में मतलब पिच इंटरमीडिएट सॉल्वेंट क्योंकि बहुत इतनी छोटी वायर में जब हम कर रहे हैं और जब हम ट्रायल कर रहे हैं एक्सपेरिमेंट कर रहे हैं तो प्योरिटी भी आ रही है, वेस्ट भी टाइम कम हो रहा है, सॉल्वेंट कम यूज हो रहा है। तो जो आपके जो रिएक्शन हो रही है तो उसमें कितना टाइम लग रहा है, सारे सॉल्वेंट के वायर में मिलेंगे तो वो आपको पूरा सेफ होगा। नैनो पार्टिकल्स को जब सिंथेसाइज करना है सिर्फ टीडियस जॉब, बहुत लंबा टाइम लगता है केमिकल स्टूडेंट्स के रिएक्शन की और वो भी फॉलो करनी है तो आती है। इसमें जब ट्राई यूनिफॉर्म क्योंकि सब तरह से हीटिंग जो है वो यूनिफॉर्म हो जाएगा। नहीं हो गया है टाइम सर, मतलब लेकिन क्या अवेयरनेस नहीं है, इसलिए रिस्पॉन्स को देख तो मिलना आप नहीं, आप अपनी फैसिलिटी को अवेयर नहीं कर सकते हैं, क्योंकि आप ट्राई कर सॉल्विंग हम जब ट्राई करना तो हमारे पास प्रोडक्ट बिजनेस से नहीं लेना आएगा, फूल भी नहीं लेना, कम सॉफ्टवेयर के साथ कम कैप्टन के साथ में हमें प्रोडक्ट
केवल 2 दिन में
कोई एक इनोवेशन नीड ऑफ द टाइम जो सैंपल होते हैं और उसके बाद जो सैंपल की जो भेजना है तो नहीं, हमने तो जो भेजे थे सैंपल तो काफी लॉन्ग टाइम की काफी भेजे, बहुत अच्छे लग रहा है जो अभी अभी करता था उससे हमने 40 और जो बहुत सही अब हमने फिर से लगाया, मतलब हमारे पास पूरा हमारे तो हम रिपीट करेंगे सेम रिजल्ट मिलेगा बिकॉज कंडीशन सब सेम कंट्रोल उसमें है, तो हमको ये नहीं है कि जब हम बिल्कुल वैसे भी करेंगे तो चेंजेस आ सकते हैं, तो जैसे वेरिएबल श्योर चल रहा है रिएक्शन का कंट्रोल नहीं एंड कंट्रोल को भाई कंट्रोल होगा डिफरेंट ठीक फाइल्स में सी वैसे भी हो रहा है रिप्रोड्यूस नहीं, ये बहुत बड़ा सर जब हमने ये वर्कशॉप करने का वन ऑफ द रीजन इज दिस आल्सो कि लोगों को मालूम पड़े, दूसरे इंस्टीट्यूशंस को भी मालूम पड़े कि हमारे पास ये है हमारे सारे इंस्ट्रूमेंट्स हैं करेंगे सर जी सर, यहाँ पे हमारे पास बहुत अच्छे अच्छे बाहर देखिए इंस्टीट्यूशन एक्स्ट्रा हमारे काफी अच्छे
मैम चला रहे हैं तो मैं ऑडियो
Welcome to the first technical session. Our next distinguished guest is Dr. Anita Dutt Kunar, a passionate researcher whose dedication to chemistry is both inspiring and impactful. We are honored to have her with us. She will deliver a talk on sustainable synthesis using microwave technology. I'm delighted to give a brief introduction of Dr. Anita Kunar, ma'am. Dr. Dutt obtained her doctoral degree in chemistry in 2008 from the University of Calcutta. Subsequently, she moved to University Bielefeld, Germany for her postdoctoral research studies. She returned to India and joined IISER Bhopal as a DST young scientist, where she continued for 3 years working on her independent DST fast track project. So far, 5 PhD students have graduated from her group, and 4 more scholars are currently working under her guidance. She has published more than 40 research papers of international journals of high repute. Her research interest not only underpins the development of peptide-based self-assembling system for biomedical applications, but also effluent management. Please join me in welcoming her with a big round of applause.
दिखना चाहिए
A very good afternoon to all of you. First of all, I am very much thankful to Varsha ma'am for your kind words. Now, I am, as you already know, hearing from the morning that I am Dr. Anita Dutt Konar from Department of Applied Chemistry and School of Pharmaceutical Sciences, RGPV, Bhopal. Now, before beginning, first I would like to extend a formal thanks to Nina ma'am, the HOD of Department of Chemistry, and all the faculty members for inviting me in this workshop. So today, the title of my presentation is Sustainable Synthesis Using Microwave Technology. Now, today I am not just here to just give a lecture and just go away. No, I would prefer an interactive session. So just look at the figure which is presented over here. Already Nina ma'am mentioned about this, that here this is a photo of a Mother Earth. Here we can see that our Mother Earth is held in the hands of human hands. On one side of the figure, you can see a note of destruction. And on the other side, that is the right-hand side, you can see it is sustainability. So the overall take-home message from this slide is, how do you want to see, or how do you want, or how do we want rather, to manage our Mother Earth? It totally depends on us, that is humans. So this is the overall take-home message from this slide. Now, can you see this figure? Here, all these have been taken from different sources of internet. So you just try to look into it. All have different mottos over here. They are of different types, figure 1, 2, 3, 4. And on the right-hand side, we have a scientist and a Cadbury bar, which is in the melted form. So what is common, or what message would I like to convey through this slide? That is serendipity. Do we know that what do you mean by the word serendipity? Serendipity means accidental discovery. Accidental discovery means it is not a planned one. No one means thought that, okay, I will discover this and then we got. No, that is not serendipity. Serendipity is a result of accidental discovery. Now let's focus on the figure 1. Can you see on the left hand side here, if you just look at the picture, Here we are all aware of Christopher Columbus. Do you know that how our America was discovered? It is a serendipitous discovery. While searching for sea routes to India, he discovered America. Then I think most of you are from chemistry background here, so you might be knowing this scientist, the blind scientist Kekulé. He discovered benzene. Do you know how this benzene structure was discovered? He just imagined that if a snake could bite its own tail, if a snake could bite its own tail, then what will happen? You can imagine of a ring structure, and that led to a breakthrough in organic chemistry, the discovery of benzene. Thirdly, just look at the figure on the figure number 3. It has been marked here. I tried to mark it. Here, it is also discovered serendipitously. How? While playing, while in a funny experiment, using a scotch tape, we all know, and graphite, this graphene molecule was discovered. I think you can identify the fourth scientist. It is Professor Alexander Fleming. He was the scientist who discovered what? Penicillin, the first antibiotic. Do you know how it was discovered? It was discovered means in a lab, unknowingly, he left a petri dish. Okay, and he forgot about it. Later on, when he entered the lab and searched, what is there any change or something? Then he found that yes, there were some molds which killed. There were some molds which killed the bacteria. In such a way, this antibiotic penicillin was discovered. But you may ask me, ma'am, why are you saying all these things? So I just want to share something which is common. So coming to today's topic, that is microwave. Okay, so here, can you see a scientist? He is Dr. Percy Spencer. He was an American engineer working in, I forgot the name of the company, but he was working with a radar. Okay, he was a very well-known scientist, sorry, not scientist, engineer, of course. And then while working with radar, once he was standing in front of the radar which contained a magnetron. What is this magnetron? It is a source which generates microwave. He had a chocolate bar in his pocket. Okay. After some time, means waiting for some time in front of the magnetron, he found that the chocolate bar melted. So this gave him the first clue for the discovery of microwave. Okay. So as a part of science, we all know that when something is discovered, you need to file a patent. And immediately he filed a patent in the year 1945, which was granted in 1950. So these are some of the tales. I am here to share with you some tales, some information, because before you start with any topic, it is always better, at least I prefer, to know a little bit of history, that how its discovery has been done. Now, coming to the next part. Now, gradually I am entering into your topic, that is microwave. So the next question that comes in mind is, where is its position is in the electromagnetic spectrum? Now, we all know Einstein's equation, E equals to h nu. We are everybody of us are aware of this. E equals to h nu, and nu equals to 1 by lambda. So what does this mean? That means if your energy is high, your wavelength will be lower, and vice versa. Now, if you look into the electromagnetic spectrum, I tried to just a minute. This is also not visible. Anyway, let me say like this itself. So if you just look at the top part of the electromagnetic spectrum, you can see an arrowhead on the left-hand side, which indicates that when you move from right-hand side to left-hand side, your wavelength increases. And As already I mentioned that wavelength is inversely proportional to energy. That means if somebody's some radiation's wavelength is lower, that means of course its energy will be higher. So which is shown over here. Thus, since microwave's wavelength is much higher, of course its energy will be much lower, and the energy of microwave is 0.00001 electron volt, which is equal to 2.45 gigahertz. Now, this energy is so low that it is not even sufficient enough to break a hydrogen bond, which is having lowest energy, that is 0.21 electron volts. Is it understandable, students, what I am trying to convey over here? Okay, thank you so much. Yeah. Next, you might be thinking, the title cannot be seen. I think it is live. ये title इसमें नहीं दिख रहा है. कोई बात नहीं, छोड़ दीजिए. It will create problem. Now the question comes, ये slide का main theme है, what is the essential condition for a molecule to be microwave active? Because हमने पढ़ा कि microwave का position कहाँ है. Now the next question कि what should be the criteria or what characteristics should be present within a molecule that is microwave active? So just one thing. For any molecule to be microwave active, it should be polar in nature. It should be polar in nature. How this polarity will help? This polarity will, I will say you. Polar in nature means you can see in the figure one positive end and a negative end. Now, the more polar is the nature of your molecule, it will align more towards the direction of the electric field, isn't it? It will align more towards the direction of the electric field. Now, the more it aligns to the direction of the electric field, the molecules will have rotation. Rotation, oscillation means various types of movements. Now, the more is the movement, what will happen? They will collide with each other, and as a result, heat energy will be generated, which will allow reactions to occur faster. So take home message from here is that what is the criteria for a molecule to be microwave active? It should be polar in nature. Next, just if you focus on the figure on the right hand side, that is, it is showing two different figures, one from the microwave one and another one a conventional. Now, I think everybody is having microwave at home, so we are very much familiar. But do we know? हाँ, we use it. हम use तो कर लेते हैं, but उसका principle जानने के लिए जब तक वो exam में नहीं आता है, हम लोग जानने की कोशिश नहीं करते. But हम सब कर लेते हैं, use कर लेते हैं. So the main difference between conventional heating and microwave assisted heating is that in microwave assisted heating, heat energy is transferred from अंदर से बाहर, inside to outside, and for a conventional heating, heat is being transferred from बाहर से अंदर, outside to inside. Okay, so this is another message which I would like to share from that figure which is on the right hand side. Now, these are some of the very common differences which we all know, that how microwave synthesis or microwave is much more preferable over conventional ones. We all know that conventional synthesis takes place a very long time, but microwaves take shorter time. Here, high energy consumption is required. That means you require high energy for conventional synthesis. But as I mentioned, since microwave is having longer wavelength, its energy consumption is lower. Then here in organic synthesis or in any other types of synthesis, we require large amount of toxic chemicals that may harm our Mother Earth. But in microwaves, either they are solvent free, and if solvents are also used, they are environmentally benign, yeah, eco-friendly, whatever you may call. Then coming to generation of hazardous wastes. Yeah, when you perform a reaction, means using conventional technology, lot of products, because nothing is in your hand, lot of products are being generated, which may be hazardous, may not be also. But in microwave, generally, it is planned in such a way that has less hazardous byproducts are being generated. And one very important advantage of microwave synthesis is that higher yields. You get higher yields and selectivity. That means if you want a particular isomer or particular thing, it is preferable that you use your microwave technologies. But in case of the conventional ones, here you have limited yields and selectivity. Now, gradually, this is just a cartoon diagram. Through this slide, I would like to convey that in conventional synthesis, generally the chemicals and other things which are used are toxic in nature, which is dangerous. But as we move towards greener chemistry, green synthesis, things become more eco-friendly. But when you move towards eco-friendly, not only eco-friendly things, when you move towards something new, there are some guidelines or some principles which drives you to that pathway. You just cannot do whatever you want. There are some set of principles. So what are they? These are 12 principles of green chemistry. I think you are already aware of, as it is there in your curriculum. But since I am here, I have been called upon I am here to just share with you just in brief. First of all, these are 12 principles of green chemistry which one should keep in mind while designing any type of synthesis. First of all, let's start from the very beginning, the topmost of the tree. So here you can find design for energy efficiency. Now, what does this mean? This means that when you design a strategy, you should keep in mind that it is always preferable that if the reaction occurs at room temperature and under normal pressures. Then coming to the safer solvents and additives, just on the left-hand side. What does this mean? That means you should design a strategy, design a synthesis scheme which involves either either no solvents, or if it is using any organic solvent also, it should be environmentally friendly. Then coming to atom economy. What does this atom economy means? Atom economy means that there should be 100% conversion. What does this 100% conversion means? That means whatever reactants you are using, that should be consumed 100% to the product. That means yield should be 100%. Then coming to prevention of waste, prevent waste, that you should design a strategy in such a way that you get minimum waste, rather toxic waste. Then coming to designing benign, safer chemicals. The word benign means eco-friendly. Eco-friendly. That means while designing any synthesis strategy, it is preferable that you choose the reactants which will not create much harm to our Mother Earth. Okay, so then use less hazardous methods. That is, it is preferable that means you use conditions which are less hazardous and having devoid of complexity. Then coming to the renewable feedstocks, your starting materials would be preferable if they are derived from renewable stocks, renewable source of energy. Then using selective reagents. Selective reagents means here, as mentioned in the principles of green chemistry, it is preferable that if you use a catalyst, because catalysts promotes the rate of reaction very faster, designed for degradation. Here, what do we mean by this? By this, we mean that we all know that whatever byproducts are being developed or generated in a particular reaction, it will go into the Mother Earth. So our design strategy should be such our design strategy should be such that whatever byproducts you get, that should do less harm to our Mother Earth. Then reduce derivatives. Okay. For this, let me try to tell you that when you want to design any drug, pharmaceutical drug, any organic compound, or whatever you want as per your requirement, you may design steps, you may design protocols which may involve a lot of steps which where intermediates are being used. So, according to the principles of green chemistry, it should be such that your design strategy should be such that less number of intermediates are being used, less number of intermediates are being formed. Then coming to pollution prevention and accidental prevention, these are self-explanatory that your reaction strategy should be designed in such a way that it will lead to less pollution to our Mother Earth, and also it will keep in mind that no accident occur. Now, as a part, then these were the principles of green chemistry. Now, how these green chemistry may be used? Is it only through microwave? No. There are several methods by which you can do green synthesis. What are they? These are some of the examples over here. First of all is the microwave assisted synthesis, which is a fast process where uniform heating is involved, less energy uses occurs over here. Second is the ultrasound assisted synthesis, which reduces reaction time, promotes cleaner reactions. Third is the UV visible light photochemistry techniques, which uses light instead of heat, avoids harsh conditions. Fourth is the use of biocatalysts or enzyme methods, which uses natural catalyst, mild conditions. Then use of supercritical fluids, which you already know, I think so, about liquid carbon dioxide, which is non-toxic and recyclable solvents. And another strategy is that atom economical reactions, which mainly involves click chemistry. It is not that only these 6 methods are there for green synthesis. There may be many, but here I have proposed these main 6 conditions. But here you can see a black circle over here. Today, our main discussion is on microwave assisted synthesis. Now, next, the question comes, हमने तो पढ़ लिया कि what are the characteristics that should be present in a molecule for to be microwave active. So, abhi, there should be some other parameters that should be kept in mind while designing a synthesis. What are they? First of all, is one very important parameter is solvent effect. That is the choice of solvent. Now, before going deeper into it, let's get introduced to 3 different terms. One is your dielectric constant, that is epsilon dash. What does this convey? It is the solvent's ability to align to the direction of the electric field. Then epsilon double dash, that is dielectric loss. That is what these 2 factors, we get this tan delta. What is this? This is loss tangent. It gives a measure of epsilon double dashed by epsilon dash. So why do we need to know about this tan delta value? The high tan delta value, just look at the top part, in top yellow part. Oh, it is not visible over here. Later on, you can see that higher is the value of tan delta, better is the heating. Higher is the value of tan delta, better is the heating, and solvents absorb microwave efficiently. Okay. Now, if you just look in the table below, here you can see 3 different types of solvents are here. One, a class which is consisting of a polar solvent, which is shown in green color, water, methanol, ethanol. Another one, a medium absorbing solvent, and the third one is your low absorbing solvent. The medium absorbing solvent is having low polarity, and the low absorbing solvent is having, they are mainly non-polar in nature. That means if you just look in the third column, dielectric constant epsilon dash, means solvents which are having means of polar nature, they are having high dielectric constants. Then the second one, they are in the medium range, and for the non-polar ones, they are in the lower range. And loss tangent value, it is clearly evident. Now, heating ability, the most important part, which you should keep in mind, that for high absorbing solvent, you will have rapid heating. For medium absorbing solvent, you will have moderate heating. And for low absorbing solvent, you will have poor heating ability. I think these are understandable to all of you. Then, that was solvent effect was one of the parameter. Then comes key, which vessel should be used for performing microwave synthesis. When we use microwave in our house for heating food, do we use metals? No. तो अभी तो जानो कि किस लिए मेटल हम नहीं यूज करते हैं. तो तीन चीज होते हैं. There are three things, that absorption, reflection, and transmission. So for any type of radiation, not for microwave. So when you irradiate anything with a particular wave, a part of the radiation gets absorbed. Second, a part of the radiation gets reflected, and a part gets transmitted. Now, तो how will we know कि कौन सा material use करें और क्यों करें? So for this, just let's focus on the figure on the right hand side, where you can see the dielectric loss factor epsilon double dashed is plotted in the x-axis, and power absorbed is on the y-axis on the left hand side. Now here you can see that agar if in the x-axis we go on the right hand side, that means if your dielectric loss factor epsilon double dashed is very high, that means वो metals होते हैं जो rays को reflect कर देते हैं. So that is not the preferable one. If you just look in the middle part, that is the absorption part, where solvents which have high dielectric constants are placed over there, generally positions them in that particular area, like water, dielectric materials, liquid resins, electrolytes, etc. And the materials which with low dielectric loss factor, that means epsilon dashed, are most preferable ones, that is alumina, Teflon, quartz, which are present on the left hand side. Is it okay? So this is the second point, that what are the parameters that you should keep in mind while designing a reaction with microwaves. Then, apart from solvents and the vessels, what other parameters should be kept in mind? That is, as I already mentioned, your reagents should be maximum polar in nature. Okay, it should be maximum polar in nature. Just look at the third point. Okay, and then it is preferable you design strategies where minimum solvents are used or no solvents are used. And if at all you cannot do that, try to incorporate solvents which are eco-friendly in nature. Then fourth one, the temperature and pressure, which should be taken care of, although it is a machine. So, but you should try to design synthesis which occurs at controllable temperatures and pressure. Then which reactions work best? Generally condensation, oxidation, reduction, CC coupling, etc., etc. It works best for microwave assisted reactions. Then I think you all are from chemistry background, or you are from different streams. Students? Chemistry. So you are familiar with this equation. Am I right? What is this? This is Arrhenius's rate equation. Am I right? Arrhenius's rate equation. तो थोड़ा तो इतना कुछ पढ़ लिया कि हाँ ये क्या क्या होना चाहिए. अभी थोड़ा देख लेते हैं कि whether we can explain the reactions with the help of this microwave Arrhenius's equation. Now, if you just look at Arrhenius's equation, where k equals to a e to the power exponential minus Ea by RT. What is this k? K is the rate constant. A is the frequency factor. Ea is the activation energy. R is the universal gas constant, and T is the temperature. you already know about this. अब थोड़ा देख लेते हैं कि how इतना टाइम जो पढ़ा रहे हैं, whether it is being able to be explained with the help of or fulfill the requirements of or can be explained with the help of Arrhenius's equation. Now, एक चीज देखो, just look at point number 1, pre-exponential factor, that is A. Now we all know that, as I mentioned, I'm mentioning it every time, that microwave reactions prefer polar molecules. So the more is your molecule polar, the more it will align to the direction of the electric field, है ना? तो जितना ज्यादा पोलर होगा उतना ज्यादा, माने सिंस दे आर डायरेक्टली प्रोपोर्शनल, तो उतना ज्यादा इलेक्ट्रिक फील्ड के साथ अलाइन करेंगे। तो इलेक्ट्रिक फील्ड के साथ अलाइन करने से क्या होगा? मैक्सिमम कोलिशन, मैक्सिमम मूवमेंट, मैक्सिमम रोटेशन, मैक्सिमम ऑसिलेशन, व्हाटएवर यू कॉल, ओके। तो जितना मैक्सिमम ये मूवमेंट्स होंगे तो इतना हीट एनर्जी विल बी जनरेटेड। तो हीट एनर्जी तुम्हारा जितना जनरेट होगा, your rate constant will be higher. That will, your reaction will be faster. Am I right? Then coming to the EA part, that is activation energy. We all know that a reaction which involves higher activation energy, so that particular reaction is slow reaction, है ना? And a reaction which involves less activation energy, unka activation means reaction rate is faster. Now polar molecules के लिए क्या होता है? Since it is polar, it aligns more to the direction of electric field. तो electric field के साथ align होने से what happens कि हाँ, it is activation energy becomes lower, क्योंकि ज्यादा पॉल्यूशंस होते हैं, ज्यादा हीट एनर्जी जनरेटेड होते हैं, एज अ रिजल्ट इट्स एक्टिवेशन एनर्जी बिकम्स लोअर। तो एक्टिवेशन एनर्जी लोअर होता है तो रिएक्शन फास्टर होते हैं। Am I right? Then coming to the third one, temperature. Temperature, although it is present, all these parameters are although present in the exponential part. Now temperature के लिए क्या है कि this is a common thing कि with every rise of 10 degrees centigrade, the reaction rate increases about 2 to 3 times. Okay, so this is the message which I would like to convey from this slide. कुछ बोलना है? Okay. Then these are gradually, अभी instrumentation के तरफ जाते हैं। अभी तो सर बैठे ही हैं, he will give नेक्स्ट, इसके बाद ही जस्ट शुरू हो जाएगा, बट थोड़ा सा एक बार देख लेते हैं कि व्हाट आर द टाइप्स ऑफ माइक्रोवेव रिएक्टर्स अवेलेबल। जो होता है बेटा सब कुछ जानना चाहिए, हम यूज करें ना करें बट जानना चाहिए कि क्या होता है। सो हियर यू कैन सी दैट देयर मे बी मल्टी मोड बैच रिएक्टर्स, सिंगल मोड इंस्ट्रूमेंट्स, ये भी दीज आर द ऑप्शंस पॉसिबल। तो you can ask me कि ma'am what are these? What is multi-mode? You are saying multi-mode, mono-mode. What does this mean? So just look in this slide. Here you can see that mono-mode microwave reactors. Now, just for any type of radiations, first of all, what you need? क्या चाहिए आपको? You need a source जहाँ से you get the radiation. So here, as you already know that from magnetron we get microwave. So for a monomode microwave reactor, we have a magnetron with a single sample irradiation. Single sample irradiation. Now you can see waveguide. So what is this purpose of this waveguide? The waveguide जो हमको guide करता है कि हमको from which way we should go. So this wave from the magnetron when means ejected, it will travel with the help of waveguide कहाँ पे? To the reaction vessel. To the reaction vessel. That means it is focused. If you look, it is a focused and it is uniform, and it is best used for precise laboratory scale reactions. तो फिर multimode वाला क्या है? Multimode means multi. Multi means, as from the name it is self-explanatory कि उधर से multiple means it is the radiation is being ejected in a multiple direction. So तो multiple direction में होगा तो उसका focus तो वैसे नहीं रहेगा. It will be it will result in a non-uniform field. In the first case, it was in a uniform field, but in the second case, it was in the case of non-uniform field. तो कहाँ पे use होते हैं? For bulk reactions, parallel synthesis, scaling up, etc., etc. अभी ऑलरेडी मैम ने पहले तो बता ही दिया एंड सर तो ऑलरेडी बैठे ही है. ही विल गिव यू अ ब्रीफ. सब कुछ अच्छे से बताएंगे, बहुत अच्छे से. मैं तो सिर्फ 2-4 फोटो दिखाने के लिए आई एम हियर. सो दिस इज द इंस्ट्रूमेंट विच इज present in this institution and which you will be using मतलब in your demonstration session. क्या है? Monowave 300 Microwave Synthesis Reactor. It looks like this. उसका एक तो कवर होता है जहां से you need to insert the things. A reaction vessel जिसके बारे में मैं already बोल चुकी हूँ. It should be resistant क्योंकि heat टेम्परेचर प्रेशर ऐसा ना हो कि ऐसा रिएक्शन तुम कंडीशन सेट किया कि वो बर्स्ट हो जाए. सो दीज आर ऑल resistant vessels, and then you should also have a thermometer which can control the temperature of the reaction what you are conducting. तो ये क्या है? आई फेल्ट कि एक इंडस्ट्रियल माइक्रोवेव रिएक्टर कैसे दिखता है. दिस इज अ फिगर ऑफ दैट. डोंट गेट कंफ्यूज्ड विद दैट. छोटे में भी जो होता है बड़े में भी सेम ही प्रिंसिपल यूज होता है, मे बी थोड़ा सा इन एन इलेबोरेट फॉर्म. तो इधर पे भी जस्ट फोकस ऑन द राइट हैंड साइड द इंस्ट्रूमेंटेशन कंपोनेंट्स. इधर पे भी एक यू नीड अ सोर्स which I already mentioned, a magnetron, a waveguide which will direct the wave from the source towards the reaction vessel. Thirdly, what you need is a chamber, insulating chamber where you will perform your reaction. Fourthly, your reaction vessels, which should be either made of quartz, glass, etc., etc., many other things which you search, you will get it. Fifthly, control systems. Control systems means you should monitor the conditions in such a way that temperature and pressures are maintained. And cooling system, कभी कभार मतलब हर चीज प्लान माफिक नहीं होता. जैसे अमेरिका डिस्कवर्ड हो गया सी रूट्स टुवर्ड्स इंडिया सर्च करने से, वैसे ही हर चीज तो अकॉर्डिंग टू योर प्लान इट विल नेवर ऑकर. तो in case some unforeseen situations occur, how to manage that? For that, you need a cooling system. Is it okay, students? चलिए, बहुत नींद आ रहा है क्या? कोशिश करते हैं कि जगह के रखने के लिए. अभी चले. अच्छा, ठीक है. अभी तो मैम फ्रॉम द वेरी फर्स्ट स्लाइड मैग्नेट्रॉन 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 बोल रहा है, बट वो ये मैग्नेट्रॉन दिखता क्या है, कैसे है, और हाउ इट ऑपरेट्स. तो उसके लिए थोड़ा सा देख लेते हैं. जस्ट ऑन द लेफ्ट हैंड साइड हियर, दिस इज हाउ अ मैग्नेट्रॉन लुक्स लाइक. ठीक है. तो अभी आप लोग सब कोई पढ़ के आए हो कैथोड एनोड ऑल दीज थिंग्स. सो अ मैग्नेट्रॉन में एक तो क्या पार्ट रहते हैं? अ कैथोड, दैट इज द ब्राउन सिलेंडर वन इन द मिडल. ठीक है. फिर एक तो एनोड रहते हैं विच इज द एनोड. एनोड विथ सेवरल कैविटीज. देखो वो ब्राउन वाला, एक गोल्डन वाला is the cathode and the brown one is your anode with resonant cavities. Then there is a magnet which will generate magnetic field which is present in the top part. देखो silver one, silver. Okay. And then there are some fins. Fins मतलब which will cool. मतलब अगर overheating हो गया or something for heat dissipation, these fins are being used. And the most important fifth part is the probe, जहां से your radiation is being released. Okay. Now working principle, ये कैसे काम करते हैं? First of all, when we know that when you apply a voltage apply करोगे तो क्या होगा? कैथोड से इलेक्ट्रॉन्स निकलेंगे, है ना? This is very common. बच्चे सब 8-9 के बच्चे, I have a son of class 8. I am teaching him. Okay. कि ये सब वो लोग पढ़ते हैं, संस्कार वैली में पढ़ते हैं वो. तो ये छोटे छोटे चीज मतलब एडवांस लेवल जो एग्जाम्स देते हैं ओलंपियाड्स और ये, इसमें सब कुछ है ऑल दीज थिंग्स. तो कमिंग बैक टू अवर टॉपिक जो मैं बताना चाहती हूँ. तो व्हेन यू अप्लाई अ वोल्टेज, तो वोल्टेज देने से क्या होगा? इलेक्ट्रॉन्स विल बी रिलीज. तो जैसे ही कोई चार्ज पार्टिकल रिलीज होता है, इफ यू अप्लाई अ मैग्नेटिक फील्ड, ऊपर से मैग्नेटिक फील्ड काम कर रहे हैं, तो दैट विल सेट दोज इलेक्ट्रॉन्स इनटू अ सर्कुलर मोशन इन द एनोड। देखो वो जो ब्राउन वाला पार्ट है, इट इज सेट इनटू सर्कुलर मोशन। तो सर्कुलर मोशन से क्या होगा? सर्कुलर मोशन, इफ द इलेक्ट्रॉन्स आर in a circular motion, it will generate a radio frequency in the microwave range, which is in the order of 2.45 gigahertz, which is appropriate for synthesis. And output, तो output क्या होगा? ये already I mentioned that using a waveguide, it will be directed towards your reaction vessel. Then और एक छोटा सा चीज इसमें, what I would like to convey that you may think कि ठीक है माइक्रोवेव में तो वैसे ही जल्दी होता है, बट इसको अगर और ज्यादा प्लीज हाँ, इसको अगर और ज्यादा फास्टर करना है तो कैसे करें? तो उसके लिए the thing is that cooling cryogenic mixture, if we circulate in the vessel, that will assist your reaction much more faster. तो आप पूछ सकते हैं मैम आप बोल रहे हैं कि माइक्रोवेव में कम हीट होता है, ये सब होता है, देन व्हाई आर यू टॉकिंग अबाउट दिस? बिकॉज इन साइंस सब कुछ आपके प्रेडिक्शन के अकॉर्डिंग नहीं होगा। हाँ, आप चाहते कुछ है, बट व्हेन यू स्टार्ट डूइंग इट, आप देखोगे कुछ और हो रहा है। इन ऑर्डर टू assure that such unforeseen situations do not occur, in such cases, अगर मान लो कि ओवरहीटिंग हो गया, तो ओवरहीटिंग अगर हो गया तो कैसे कंट्रोल करेंगे? सो इट इज बेटर टू सर्कुलेट दिस क्रायोजेनिक मिक्सचर which will cool your reaction system. Secondly, advantage ये होता है कि there may be certain molecules, your reactants, which may not be or which may undergo degradation at higher temperature. So in order to control or maintain its biocompatibility, biodegradability, this cryogenic mixture circulation is important. इस स्लाइड से इतना ही। Now, अभी तो इतना थ्योरी तो पढ़ ही लिया है, अभी थोड़ा सा देखते हैं कि how this microwave synthesis reactions are advantageous over the conventional ones. Now we all have studied in our lower classes about the nucleophilic substitution reactions. पढ़ते हैं ना, SN1, SN2, ये सब फिर elimination reactions. तो just it is an example which is also taken from some standard textbooks. I forgot. My student, I will acknowledge him later on. He has taken, मैंने उनको बोल दिया था कि I need this, तो उन्होंने मुझे ये कर दिए हैं। So ये न्यूक्लियोफिलिक सब्स्टिट्यूशन रिएक्शंस अगर आप देखेंगे कि इन द सेंट्रल यू हैव स्टार्टिंग मटेरियल एंड फ्रॉम इट डिफरेंट डेरिवेटिव्स आर बीइंग produced. But what is the main thing what I would like to say? When these reactions were carried out conventionally, मतलब नॉर्मल कंडीशंस में, तो टेम्परेचर 100 डिग्री सेंटीग्रेड लगा था, but time taken was 12 to 24 hours for different derivatives and the yield was very, very low. That was 35 to 60%. When the same reactions were carried out in microwave, although the temperature was 175 degrees centigrade, but the reaction got completed within 10 minutes and 100% yield was obtained. Then coming to a different synthesis of six-membered rings. Six-membered rings are very important precursors of drugs, okay? Drugs or in pharmaceutical industries and many more applications, okay? So I felt that if some examples can be given, so students may find helpful for it. So first of all, if you just look at the synthesis of quinoline, can you identify the heterocycle? That is simple, quinoline. Quinoline क्या होता है? बेंजोफ्यूज्ड पिरिडीन, मतलब बेंजीन के एक कार्बन को अगर नाइट्रोजन दे दिया, दैट इज पिरिडीन, और उसके साथ एक रिंग अगर लगा दिया, बेंजीन रिंग, दैट इज बेंजोफ्यूज्ड पिरिडीन, दैट इज ओनली quinolines. Now here X means data reveal that when this reaction was carried out Under conventional conditions, the yield was very low. But in microwave assisted synthesis, means microwave, when it was performed under microwave conditions, the yield was 80 to 87%. That was significantly high. Then coming to another famous reaction, hand synthesis. Hand synthesis for the another synthesis of pyridines. Here also, data reveal that here, for conventional cases, 12 hours reaction used to take place, and that also with only 15 to 16% yield. But in case of microwave reactions, the reaction got completed within 10 to 15 minutes with almost 100% completion. Then coming to decarboxylation of 6-methyl indole 2-carboxylic acids. Simple dekho, if you just look at the reaction, just a molecule of carbon dioxide got eliminated. तो इसमें कैसे हुआ? तो microwave synthesis में it got completed within 12 minutes. Then oxidation of toluenes, ये तो हम सब जानते हैं, to benzoic acid. This reaction normally it took about 10 to 12 hours. But in case of microwaves, it just got completed within 5 minutes. Then hydrolysis of methyl benzoate to benzoic acid. That is, it is a simple hydrolysis reaction. This reaction got converted into 2.5 minutes completed. Then coming to the microwave assisted Hoffman elimination, I think you are all bachelors, masters, I don't know which grade students, so you are aware of these elimination reactions, Hoffman, Sedzev, etc., etc. So this is the class of Hoffman exhaustive methylation reactions where eliminations occur, and this elimination in microwave just took only 1 minute for its completion. Another category of 6-membered ring compounds. Now, one very important reaction nowadays is Diels-Alder reaction. Are you aware of pericyclic reactions? Diels-Alder reaction, which involves a dienophile and a diene. So it has been noted that these Diels-Alder reaction, which earlier took long time for its completion under conventional conditions, just completed in 90 seconds. Similarly, synthesis of pyridine derivatives, so big derivatives, but getting converted within 3 minutes, 2 minutes, etc. Then the acid catalyzed synthesis of 6-amino 3,5-dicarbonitrile 2-thiopyridines, which is nothing but another pyridine derivative. This reaction for normal cases, it took 2 to 2.5 hours, but in microwave, just hour to minute. That means less time. Synthesis of 5-membered ring compounds. This is also very important. This here I have not discussed all, just the very important ones. Imidazoles. Imidazoles are very important class of compounds from the perspective of heterocyclic chemistry. Now, imidazole synthesis, conventional cases took 4 hours, but in microwave, it got converted within 10 minutes. Then synthesis of pyroles using Palnor synthesis. So here, pyrrole conversion got completed very fast within 2 minutes. Synthesis of triazoles. This is also an important nucleus for Alzheimer's disease, which I am currently working on. One of my students already got PhD under me working with these triazoles. So I thought that let me take that example. Then synthesis of 4,5-dihydrocarbothiamides. This is another class of heterocycles. Here also the reaction took place very faster. Then pyrazole synthesis here also, in comparison to the conventional ones, reaction got completed within 3 to 5 minutes. And lastly, this is the another, do you know if N and N are present close by, what is this nucleus called? If in a 5-membered ring, N and N are present in alternate position, it is imidazole. Okay. If they are present 1-2 position, that means adjacent to each other, it is pyrazole. Okay. So pyrazole is also an important nucleus here. So using microwave synthesis, you can perform all these type of reactions. Oxidation of primary alcohol about the workshop. So very important use of microwave is in the design of nanoparticles. So you may ask me how this nanoparticle will be useful. Dekho, it is not that you cannot generate nanoparticle using other techniques. You can generate, but the most important thing is that here uniform heating is being used in this technique. तो uniform heating होने के कारण the size controlling, you can have a precise control over the size of the nanoparticles. और इधर पे what you get is that you have uniform distribution of size. Uniform distribution of size of the nanoparticles. For example, silver nanoparticles are being generated many times. There are lots of references. Lot of work are being done on these fields using these microwave reactors. Then coming to peptide synthesis. So although I am a peptide chemist, I don't use microwave synthesis, but it is a very useful technique. How? Because in peptide synthesis, I don't know whether you are aware of, we require a lot of protection decryption steps. If this techniques can be used, the time can be shortened. Then microwave assisted organic reactions, Suzuki, Miura, and many other things, all these have been reported using these techniques. Then some other techniques like polymer chain reactions, where you can do DNA extraction using microwave assisted lysis. You can also use ionic liquids. As I mentioned, that polar molecules works excellent in this technique. Then इतना तो अभी और सो मत जाना, और 5 मिनट में आई विल कंप्लीट. नाउ इतना तो सब हम जान गए हैं, मेरिट्स है इतना, तो हर टेक्निक का मेरिट्स जैसे होता है, कुछ कमियां भी तो होते हैं, तभी तो साइंस का एडवांसमेंट होगा, है ना. देन ओनली साइंस विल प्रोसीड, बिकॉज साइंस कभी रुका नहीं जाता, इट ऑलवेज प्रोग्रेसेस. आज जो नया है, टुमारो इट विल बिकम पुराना. It will means उनके ऊपर डेवलपमेंट होगा, then only science progresses. So what are these coming to the merits? Already we know, according to the principles of green chemistry, कि fewer steps are required, energy efficient techniques, solvent free conditions. ये तो मैं बहुत बोल चुकी हूँ. थोड़ा बहुत demerits के बारे में बता देते हैं. Demerits के बारे में the most important thing, सबसे जो जरूरी होते हैं पैसा. सबसे जो जरूरी होते हैं पैसा. सो इट इज नॉट एट ऑल मीन्स इट मीन्स कॉस्ट इफेक्टिविटी पर्सपेक्टिव से इसका इंपॉर्टेंस थोड़ा. देन इधर पे कुछ केसेस में, जैसे मल्टीमोड हीटिंग टेक्निक्स में नॉन यूनिफॉर्म हीटिंग इज बीइंग यूज्ड. कभी कभार सॉल्वेंट, ऑल्दो कि सॉल्वेंट यूज इज यूज्ड in minimal quantities over here, अगर solvent use हो गया तो उसका evaporation it is sometimes very difficult to control. So that is another side reactions and degradation control and be kept in. तो हो जाएगा, तो इसके लिए how the things can be led to progression. First of all, that conclusion perspective में, these are faster reactions with higher efficiency, reduces energy consumption and waste, enables precise control over reaction parameters, supports green and sustainable chemistry approaches. Future aspect, key scaling up is to be taken care of. Then fast and selective reactions, combination with AIs. आजकल तो सब solutions AI से मिल जाते हैं. तो अगर दो बुद्धि मानी AI के साथ दो चीज को combine किया तो more advancement can be done. And further exploration of how to use completely solvent free conditions should be taken care. So these are the references from where our slides are being prepared. And after all, this is my research group. ये जो मैंने बोला कि 5 students have already been graduated, जिनका हो चुका है, Dr. Priyanka, Dr. Arvind, he worked with triazole systems, Dr. Noreen, फिर Dr. Ankita and Dr. Radha. और मेरा current research group है, which is there here. Rishabh from the left, he will be submitting his thesis with this year, submit his thesis, and two other students, Suren standing in front and Deepesh. You can see one circle around the person, Deepesh. He is my student who helped me in preparing the slides. So I am extremely thankful to him. And after all, thank you all audience for your kind patience. Abhi lunch time hai, but still you have showed enough patience to listen to it. Thank you for everything. Okay. ये लेने में चलना क्योंकि भूल जाऊंगी फिर.
Thank you for this wonderful presentation, ma'am. I'm confident that the ideas exchange here will help us to significantly step forward towards a safer world. May I request Dr. Neena Arora, ma'am, to kindly present the memento to our speaker, Dr. Anita Dadkular, madam.
नहीं चल रहा था अभी नहीं चल रहा हमने तो उससे करा है सब कुछ नहीं दिख रहा आप लोग कोई ठीक इधर दिखा नहीं तो आप तो दिख रही हो.
Through the lens of modern tools like Monowave 200 Microwave Reactor, we unlock new ways of making chemistry. Next, we invite Mr. Vikesh Chauhan from Anton Par to highlight the role of technology and industry in advancing sustainable research. Mr. Vikesh is working with Anton Par for the past 11 years and has 7 years of experience in the field of microwave synthesis. As an industry expert, he brings with him a unique perspective on how cutting-edge technology supports and empowers modern chemistry. Vikesh, sir, welcome.
Nice meeting you. Thank you for all of you. And I'm okay, bye-bye, students. Bye.
Hi, good afternoon, everyone. So I know it's lunchtime. I won't be taking much of your time. So I would like to introduce myself. I'm Vikesh Chauhan. I'm working with Entenpar India as a regional sales manager for Northern region. for the analytical and synthetic chemistry division, where we have instruments like microwave synthesizer and microwave digestion system. So first of all, I would like to thank Dr. Nina, Dr. Varsha, and other faculty members for organizing such informative workshop and giving us the opportunity to present our product portfolio and specifically microwave synthesizer instrument. So just a brief introduction about Entenpar. So Entenpar is a company founded by the Santner Foundation in 1922. So it's a more than 100-year company. Its headquarter is in Graz, Austria, which is in Europe. And in India, we are...
Sorry, to share screen.
So in India, we have our headquarter in Gurgaon. Entenpar has more than 39, Entenpar has its presence in more than 39 countries across the globe. We have more than 4,500 employees across the world. Entenpar invests its more than 15% share of profit share in R&Ds, research and development of new technologies, new equipments. This is the product portfolio of Entenpar. So we have instruments related to density and concentration measurement. So Entenpar is the inventor of first digital density meter in the world, which is invented more than 50, 60 years ago. We have instrument related to viscometry, rheometry, sample preparation and synthetic chemistry, XRDs, polarimeter and refractometer, Raman technology, FTIR, surface area and pore analysis, gas analysis. So this is the product portfolio. We have more than 200 plus products in our portfolio. So today I'm going to talk about synthetic chemistry product portfolio. So first of all, my slides were of some basics about microwave and how it works, but Dr. Anita has already covered it. So would you like me to repeat it or should I skip the same? Okay. Okay, so this is just the basic, the Arrhenius equation, where you know that every 10-degree increase. So in microwave chemistry, we use this Arrhenius equation where it says every 10-degree increase in temperature will double your reaction rate or will reduce the reaction time by half. So if you are performing any reaction at suppose at 120 degrees Celsius, 8 hours, if you are able to go to 130 degrees Celsius, your reaction can be completed within 4 hours. So subsequently that. So this is the way of heating. This is conventional heating where the surface of the container will be first heated, then the heat will be transferred to the sample or the mixture inside the vessel. But in microwaves, the microwaves does not heat the container. It directly heats the mixture or solvent or reactant, whatever is inside the. So it's a direct heating or faster heating. The control of this microwave heating is very fast. So it can be instantly switched on or switched off, unlike the conventional heating. So this is microwave, dipolar reduction, rotation, and ionic conduction. So these are two types of heating technologies. So classification of solvents as described by Anita ma'am. The solvents are classified based on loss tangent, right? So it's ability to absorb the microwaves. So microwave solvents are classified as polar solvent, non-polar solvent based on the absorbance. It's absorbance. So practically we say that we in microwaves the non-polar solvents cannot be heated. But this is with Entenpar. You can use non-polar solvent in Entenpar microwaves. We have the technology because we offer the highest power, a microwave power of 850 watt. You won't find any microwave which has more than 400 watt or 400 watt, more than 500 watt power in their instrument. We offer 850 watts, so which provides more than 6,000 watts per liter field density, and we can achieve we can heat this non-polar solvent, whether it's chloroform, hexane, toluene. So we can go above 200 to 50 degrees Celsius. We can reach. So this is the microwave synthesis product portfolio of Entenpar. So as ma'am explained, there are two types of microwave reactors, monomode and multimode reactors. So in the left-hand side, you can see the single vessel reactor, which is Monowave 200, 400, 450, and 400R. This is the monomode instruments. And then we have multi-vessel reactor, which is Multiwave 5001. So this is the applicable reaction scale with Entenpar products. So we have this 96 position rotor where you can work from 0.3 ml to 0.3 ml to 3 ml reactions. So this is for our R&D scale or library generations. Then we have monomode reactors, which has a working volume of 0.5 to 20 ml. This is from some small milligrams to gram scale. And then we have this Multiwave 5001, this which is parallel synthesizer multi-mode reactor, where you can go to multi-gram scale. So about the Monowave 200, which is already installed in your college. So this is the Monowave 200. So basically, this microwave has few components. So one is magnetron, which is the source. Then we have IR sensor, which measures the temperature, right, of your reaction. Then we have pressure sensors, uh, uh, which measures the pressure inside your vessel. So it has wireless measurement of temperature, right? And Monowave 200 has installed power of 850 watt and output power of 850 watt. Working temperature is 260 degrees Celsius, and it can hold up to 20 bar of pressure. It has inbuilt magnetic stirring from 0 to 1200 RPM. So it requires an air compressor for the cooling purpose, and magnetic stirring is also there. We have optical fiber sensor also, which is Ruby thermometer, which ma'am has also shown you in the picture, which will be a kind of a probe which will be inserted directly inside your reaction. So there are reactions which are very aggressive in nature, or which are where the temperature rises very sharply, or if we are using catalyst which make the reaction very fast, so where the temperature shoots up very fast. So at that time you might require this Ruby thermometer, which is inside the sample reaction. So this Monowave 200 can be upgraded to Monowave 400. So Monowave 400 is an instrument which is exactly like Monowave 200, but it has only three unique features, which is Monowave, the working temperature goes from 260 degrees Celsius to 300 degrees Celsius. The working pressure goes up to 30 bar from 20 bar, which is in Monowave 200. And then it is 21 CFR compliance also. And it has inbuilt camera option. So Monowave 400 has camera where your reaction can be seen. You can see the reaction on screen. You can take the picture of your reaction. You can record. So this is the only difference between Monowave 200 and 400. So these are the type of vials which are being, or I can say consumables, which are being in used, Monowave 200, 400, all those instruments. So we have this vial 4 ml, 10 ml, 30 ml, and 30 ml wide neck. So 4 ml vial has working volume of 0.5 to 2 ml. Then 10 ml vial has working volume of 2 ml to 6 ml. Then 30 ml vial has working volume of 6 ml to 20 ml. So your working volume within the instruments starts from 0.5 ml and it goes up to 20 ml. These are the consumable silicon septum and snap caps, which are required to close the vessels. So this is the optional silicon carbide vessel, which is in 10 ml and 30 ml vials. So these are the vials which is only with Enten par. So this is required only for the special reactions, the reaction which are not compatible with glass. Like if you want to use any kind of hydroxides, right? If the reactions has fluorinations, the fluorination reactions, so where you cannot use the glass because it will attack fluorination will attack the glass and it will be broken. So for those kind of reactions, you can use these silicon carbides. So this is just an example of fluorination reaction. If you perform this fluorination reaction in the glass vials, you can see in the picture what will happen to your glass vial. So this is camera where you can see in the on-screen camera. You can take the picture of your reaction. You can see if there is any precipitation, color change, or if you want to record your complete reaction, you can do the video recording of your reaction as well. So this is the IR sensor, which is placed at the bottom of the vial, which will measure the internal temperature of your reaction. So it will do the measurement wirelessly. So stirring. So importance of stirring, you can see in the picture, the stirring is very important for uniform heating across the reaction. In the glass vial, you can see we have placed 4 different sensors. We have switched on the stirring in between. You can see at one place, the temperature is about 100 degree. At one place, the temperature is about 130, 140. At one place, it is about 170, 180 at the bottom, right? But when the stirring is on, the top, middle, bottom, IR, everything is same. So this shows that stirring is very important for uniform heating in the entire reaction vessel. Then we have another model which is Monowave 450. Monowave 450 is exactly same like Monowave 400, but with an additional auto sampler for unattended operation. So you can just plan your reactions. So you can plan up to 24 reactions in this. Just put your reaction, program it, start it, and you can leave. So you can leave, you can keep it unattended for the whole night. Once you come in the morning, all your reactions will be automatically done. Cooling, everything will be done, and you can see in the morning your reactions are completed. So all these models are upgraded. Monowave 200 it is possible to upgrade Monowave 200 to Monowave 400. Monowave 400 can be upgraded to Monowave 450. So all these models are upgraded. We have another model which is Monowave 400R. It's exactly same like Monowave 400. The difference is it doesn't have any camera, but instead of camera, you can insert the Raman probe for the in situ measurement of your reactions. So while your reaction is going on, you can do the analysis of your reactions through the Raman spectrophotometer. Sorry. Then we have this Multiwave 5001 instrument, which is a parallel microwave synthesizer, multi-mode instrument, we can say. So this is for the scale-up reaction. So once you have optimized your reactions in the small scale monowave, if you want to go to multi-gram generate high quantity of your reaction, you can use this Multiwave 5001 for scale-up. It has installed power of 2000 watt, which is more than almost double of Monowave 200 or 400. The working temperature pressure here will be 260 degrees Celsius in 20 bar, which is the highest. And these are the kind of rotors applicable. So this is 16 position and 8 position rotor, where you can plan 16 reactions in a single go, right? So 16 vessels will be there. Each vessel can be filled up to 60 ml, minimum 6 ml, and up to 60 ml. So total working volume goes up to 960 ml, so approximately 1 liter. Sorry. And it has working temperature of 250 degrees Celsius and 40 bar. And then we have 8-position rotor where Teflon vessels, it's all, this is also 100 ml, but it has high temperature up to 260 degrees Celsius and 60 bar. So these there are some special accessories as well available with this Multiwave 5001, where you have this gas loading accessory. For example, if you want to plan your reaction in certain atmosphere, like inert atmosphere or something like that, you can use this gas loading accessory to purge the gas inside your reaction, and then you can start your reaction. And these are silicon carbide elements just to heat up the non-polar solvent in this. Just few examples of organic reactions. There are different kind of reactions you can perform in this microwave: organic, nanomaterial, polymer, and special applications. So this is just an example. Yeah. So this is just an example of one organic reaction where माइक्रोवेव सिंथेसिस के साथ आपने एक पॉली फिनाइल डाइअमीन प्लस एसिटिक एसिड यू हैव यूज्ड, and with at 260 degrees Celsius, 270 degrees Celsius, you heated it up, and within 1 second, this reaction is converted into 2-methyl benzimidazole, sorry, in within 1 second. Yeah, sorry, I'm not a chemist, so this is quite difficult for me. You can see in the table at 25 degrees Celsius, this reaction is taking approximately 9 weeks to complete. When it is 60 degrees Celsius at atmospheric pressure, it takes 3 days to complete the reaction. But as you are doing it in closed vessel, when the pressure is generated, 2 bar, 4 bar, 9 or 29 bar, you can go up to 70 degrees Celsius, and within 1 second, this reaction is completed. So this is an example of iron oxide nanocrystals, where you can see the reaction is iron complex. Then octadecane and oleic acid is used, and you can see Fe3O4 is generated within 15 minutes of the reaction. Then we have polymer, example of some polymers, where you can see this is the PET bottles, right? So this is basically used in plastic bottles, polyethylene terephthalate. So this is treated with data and in Monowave 200 Monowave, and at 200 degrees Celsius and 1 minute, you can see this is converted into aminolysis product, which is transparent yellow solutions. So you can follow this synthetic chemistry channel on LinkedIn for such kind of reactions. There are numerous reactions which are published in this paper. You can follow this, the LinkedIn profile. That's it. If you have any question. Yes, ma'am. Ma'am, you don't need to, because the instrument is designed in such a way that the microwave leakage will be less than 5 dB. right? And once the engineers during the AMC or service visits, he will have a microwave leakage tester, and he will test that if it doesn't go beyond that limit. Yeah, thank you. Yes, ma'am, please. Ma'am, you cannot. In Monowave 200, you cannot. In Monowave series, no, one or two drops, but it can harm because it is not designed to use HCl or H2SO4 kind of because these are corrosive in nature. But in like it is not designed in Multiwave 5000, which is designed for the acidic use also, where you can use even 10 ml or 50 ml of H2SO4, HCl, nitric, any kind of acids. So this is designed only for solvents. Ma'am, see, it's not that H2SO4 is compatible with the glass. It's not about the glass or silicon carbide. It's the instrument design for solvents only. You can use one or two drops, it won't harm. But if you use it continuously, it might, if there is some kind of leakage or some vapors are released in case, then it will damage the cavity or the electronic of the instrument. You can go to room temperature. So you starts from, if the temperature is 25-30 degree, you cannot go below that. So if the temperature is 30-35 degree, you can go 40, you can start from 40-45, something like that. Thank you. Thank you so much.
Thank you, Vikesh ji, for sharing industry expertise that connects innovation with practical solution. A memento is a symbol of remembrance, a way to carry the memory of today's academic exchange. I request Dr. Neena Arora, Madam, to present a memento to Mr. Vikesh Chauhan. Thank you, ma'am. With the morning session coming to a fruitful close, let's now take a break and disperse for lunch. After lunch, we will assemble in FIS lab for technical session 2 and practical session also.
Yeah.
नहीं हो पाएगा नहीं होगा बस
नहीं ऐसा कि आप इसको इंस्ट्रूमेंट पे फोकस कर लो बाकी तो आवाज में चली जाएगी पास
आप कहाँ खड़े हो गए
चलिए मैं करूँगा मैं इस साइड खड़ा हो जाऊँ
हाँ
दूसरी जगह से ये बस तो वो दिख रहा है इम्पोर्टेंट
मेरा दरवाजा बजा ठीक है मैम सबसे पहले वाला जो पार्ट उसको सेकंड लेवल से है तो आप पूरा एक सेकंड आप लोग कुछ आगे लो आगे
क्या language. हम स्टार्ट करो स्टार्ट करो बता दीजिएगा जब एक माइक एयर बैठे बैठे माइक चला अरे ठीक है पीछे तेरे आवाज नहीं पहुंच रही। अरे पहुंच गई अभी बोले नहीं मैं बच्चों को देखने देना है अरे बोले हेलो गुड आफ्टरनून आई होप आपका लंच अच्छा होगा सो we are here for the live demonstration of the instrument. So first of all, I'll brief you about the instrument, right? So starting from the back side, there on the left hand side, there is a power switch on, switch off button, and you will have to plug the cable on the back side of the instrument, power cable, right? Then there is another connection on the back side, which is for connecting the compressed air supply. So here is a compressor. So this compressor is connected to this tube. You can see this pressure regulator. So it requires a 5.5 to 6 bar of continuous air supply, compressed air supply. It should be dry air, right? Which is connected at the back of the instrument. So जब भी आप instrument start करेंगे, कोई reaction लगाएंगे, make sure that along with the instrument, the air compressor should also be switched on, right? अदरवाइज अगर आप रिएक्शन लगा दोगे एंड कंप्रेसर आपका बंद है सप्लाई नहीं है इंस्ट्रूमेंट विल गिव यू एरर दैट नो कंप्रेस्ड एयर सप्लाई सो उसके लिए आपको देखना है यू नीड टू मेक श्योर कि यहाँ पे 5.5 to 6 बार का एयर सप्लाई हो ठीक है
नहीं इन एंड आउट प्रेशर यहाँ से मेजर हो जाता है इन प्रेशर जो जा रहा है इन एंड आउट प्रेशर एक डायरेक्शन
So at the back you can see this is the power switch on switch off button. This is the power cable connection. This is the exhaust pipe. If there is any fumes generated during the reaction and during the cooling, these fumes will be removed from the instrument through exhaust fans by this exhaust pipe. And this is the compressed air supply where it's written 5.5 to 6 bar. So you need to connect this hose here. So during the installation, this hose is connected for the air supply. So this is the back side of the instrument. So at the front, this green LED indicator shows that power is there. In case the display is not coming, you can see the switch on. In case you have switched on the instrument is not getting switched on. You can see with this LED whether the power connection is connected or not. It might be there that you are switching on, but backside the cable is not there. That means there is no power supply. So it shows the power supply there. This is the display which we use to display all the reaction parameters like temperature, pressure, stirring, time, कितना आपका reaction हो गया, all those kind of things. यहीं से you will do your programming. There is no external software or computer needed for this. It has pre-installed software in this. And this is the red color cavity, right? And you will plan the reaction. जहाँ पे आप अपना reaction file रखेंगे. Once you start the reaction, this red color cover, which is called as swiveling cover, goes to the back side and it is closed. So this cover will be closed जब आपका reaction start होता है, and it will be opened once your cooling temperature जो कि आपने programming में set किया है, once the reaction temperature is cooling temperature is reached. It's open only after that. उससे पहले ड्यूरिंग द रिएक्शन अगर आप करते हो तो इट विल नॉट ओपन, राइट? सो आपको रिएक्शन एक्सेसिबल नहीं होगा जब आपका रिएक्शन चल रहा है. So the display shows after you, this is your home screen. At the top, you have this name, which is no experiment. So आप यहाँ पे आप whatever reaction you plan, you give a name to your reaction. वो नाम यहाँ पे display हो जाएगा जो भी आप reaction कर रहे हो. This is the green symbol, which is the status symbol. So if you take this, changes this green changes color, its color to, into three colors. This is green, yellow, or red. Right. So green is that, so everything is fine. No, there is no warning, no alarm, no error in the instrument or during the reaction. If it is yellow, that means there is some kind of warning is there for you. And once you click on this, the message will be displayed. What kind of warning is there? It might be कि आपका compressed air का pressure drop हो गया है, कुछ हो गया है. So just a small warning. If there is any fault in the instrument or fault in the reaction, आपका कुछ भी अगर गलत हो जाता है, so it turns into red color. So जहाँ पे आपका message display हो जाता है, then you can see कि मेरे instrument में क्या problem है, whatever you can identify for this. Then there is a graph. So this graph, on the left hand side, you can see the temperature is there. At the bottom, it's time. The right hand side, there are two parameters, which is power and pressure. So instrument has 850 watt of installed power. Right? So जब आप synthesis करते हो तो you might see in the reaction old research papers आपको power based programming भी मिलेगा, and the research paper you will see also a temperature based programming. So programming आप दो तरीके से कर सकते हो, based on power and based on temperature. पावर बेस्ड प्रोग्रामिंग आपको मिलेगी जब पहले लोग यूज करते थे, जहाँ पे लोग डोमेस्टिक माइक्रोवेव्स यूज करते हैं मोस्टली, या फिर पहले जो माइक्रोवेव्स होते थे उनमें पावर बेस्ड प्रोग्रामिंग होती थी, टेम्परेचर बेस्ड नहीं होती. सो पावर बेस्ड प्रोग्रामिंग का एक इशू है. देयर इज एन इशू विद द पावर बेस्ड प्रोग्रामिंग, व्हिच इज द पावर बेस्ड प्रोग्राम्स आर नॉट reproducible. And why is that? So suppose I'm giving 1000 watt of power for a reaction in this instrument, which has a cavity of approximately, I think, 1 or 2 liters, right? आपका कोई दूसरा microwave है which has a cavity of approximately 10 liters. If I give you 1000 watt in that reactor, that power might not be sufficient to reach that temperature, right? So उसमें पावर बेस्ड टेम्परेचर डिपेंड्स आपका कैविटी साइज क्या है, वॉल्यूम आप कितना ले रहे हो. सपोज यहाँ 10 ml ले रहे हो, अगर आप 1000 वॉट के साथ ही आप किसी दूसरे रिएक्टर में 50 ml को हीट करोगे, दैट पावर माइट नॉट बी सफिशिएंट, देन यू अगेन नीड टू रीऑप्टिमाइज योर रिएक्शन. बट जब से ये टेम्परेचर बेस्ड प्रोग्रामिंग आई है, अगर आप इसको भी 250 डिग्री सेल्सियस पे कोई रिएक्शन 10 मिनट में कर रहे हो, चाहे वॉल्यूम 2 ml है, 10 ml है, डजंट मैटर, आप किसी भी माइक्रोवेव रिएक्टर में वो दुनिया में करो तो 50 डिग्री सेल्सियस पे दैट रिएक्शन विल बी कंप्लीटेड विद इन 10 मिनट्स. सो दोस प्रोग्राम्स आर रिप्रोड्यूसिबल. कोई डाउट इसमें कुछ?
Sorry. Sir, you can.
Okay.
Sir.
Then next is task list. So how to do the programming? आप अपना program कैसे set करोगे? क्या method set करोगे? So you just go on the task list. There is a number of methods, programs which were already run on this instrument. So वो आपको display हो जाएंगे. You have two options. आप कोई भी previous method लीजिए, उसको highlight कीजिए, and then just do the copy. Then अगर आप उसको copy करने के बाद आप उसको edit कर सकते हो simply. Suppose I'm editing this. I keep its name as test. Okay. Then I click on these three dots to change my program. मैं पुराना जो था उसको select किया just, मैंने उसमें जो भी editing करना है editing करना. So then so first यहाँ पे हम है हमारे पास glass lines. So have these glass lines. This is 10 ml glass line. It is called a G10. This is 30 ml glass lines. This is called G30. Then we have this black color also, which is not available at the moment, silicon carbide, which will be C10 or C30 depending upon its one, right? So this is the 10 ml vial. But आपको अपना reaction plan करने के लिए क्या क्या चाहिए होगा? You need this 10 ml vial. You need this lab cap. Then you need this silicon septum, and you need a stirrer. So in the 10 ml, you can put minimum you have to put 2 ml. Maximum you can fill this vial up to 6 ml. So this is the magnetic bead. So आप अपना इसमें जो भी आपका solvent reactant mixtures होता है वो आप उसमें fill कीजिए. Then put this magnetic bead. Then this septa has two different colors. So at the top अगर आप देखोगे तो it's blue और किसी और color में भी हो सकता है. At the bottom it's white. So what you need to make sure कि आपका ये जो septum है, this is PTFE coating septum, right? So it should always be at the towards the bottom side. क्योंकि ये reaction mixture की तरफ होना चाहिए. अगर आप ऐसे भी करोगे problem कुछ नहीं है, but क्योंकि ये silicon का है, ठीक है, आपके reaction में कुछ right. So आपको ये हमेशा रखना है जिससे आपका कोई contamination और ना. So you just fix this septum into this lab cap. Simple way. Then you just at some angle keep it there like this and press it.
Just from thumb only, don't directly extend.
Don't do it like this. Ki straight rakha, you press it. It will not go like that. So thoda sa angle pe liya and then pressed. This is closed now, right?
And for opening, same like that you have to do.
So if you want to open the now reaction, जब आपका cool down हो जाता है, simple. एक angle पे ही इसको दो फिर अपने thumb लेके push कीजिए.
बस
Very simple.
Distance रखते हुए.
ठीक है? आपका ओपन आप तभी कर पाओगे जब कूलिंग कंप्लीट हो जाएगा. उससे पहले आप ओपन कर ही नहीं सकते क्योंकि एक कवर क्लोज हो जाएगा, आपको एक्सेसिबल ही नहीं है. जब आपका कूलिंग टेम्परेचर जो सेट किया है वो आएगा उसके बाद आप कर सकते हैं.
टेम्परेचर सेंसिटिव रिएक्शंस तो इसमें कैरी आउट कर सकते हैं. टेम्परेचर सेंसिटिव रिएक्शंस जैसे एक पर्टिकुलर टेम्परेचर पे ही वो रिएक्शन स्टेबल रहता है. आफ्टर द वेरिएशन इन द टेम्परेचर दैट रिएक्शन विल गेट कन्वर्टेड बैक टू रिएक्टेंट्स. ऐसे कंडीशंस में क्या इसको यूज कर सकते हैं?
मेक श्योर कि आपका जब जो भी आपका है रिएक्शन है need to optimize it. Basically it's kind of optimization only. This is the optimum temperature or this is the optimum
Okay, I
time
have to
for
select the range.
So you have to do that. Your optimization. For particular, you can do any kind of reaction there, right?
Okay.
But it's synthesis. So इसमें problem ये आ जाती है अगर आप suppose high temperature पे expose कर देते हो किसी temperature.
एंड वो आपका क्वालिटी डिग्रेड होना शुरू हो जाता है रिएक्शन का। तो अगर आप वो करोगे तो कोई भी है वो आपका, सो यू नीड टू मेक श्योर यू ऑप्टिमाइज इट।
सो मुझे पहले वैलिडेट करना पड़ेगा। ओके,
ठीक है। सो इफ देन देयर इज दिस ring basically. So if you are using 10 ml vial, you need to use this ring. Without this ring, you cannot keep the vial inside this cavity. So it has two sides, flat surface है और थोड़ा सा. So you need to make sure कि आप जो flat surface है इसको नीचे रखो, इसको ऊपर. So आपका जो vial जाएगा, will hold this vial like this. Right? And this is applicable only for 10 ml. If you are using 30 ml vial, simple same आपका snap cap, same septum 30 ml vial में use होगा. Same सब, you don't need separate consumables, separate items for this. If you are using this, okay, so same consumables you need. आप 30 ml vial को directly instrument के अंदर place कर सकते हैं. ठीक है. Then for the programming, you need to select which kind of vial you are using और जो आप program बना रहे हो आप किस vial के लिए है. So it's there G40, G10, 30 and SIC vessel. So suppose I'm making my program for this 30 ml vial. I select G30. Then there are 3 steps. Basically, synthesis के लिए आप 3 steps programming करते हो. So first step is heat to temperature. So first step will always be heat as fast as possible. Then you have the option of heat to temperature in time, and then there is a third, which is constant power. So, as you asked,
Constant power.
now the first step, have heat as fast as possible, heat to temperature in time, and then third, constant power. Okay, so heat as fast as possible is that you have a target temperature of suppose 150 degrees Celsius. So you are not giving it time, you are asking the instrument to reach 150 as fast as possible. So it might take only 15, 20, 30 seconds to reach that temperature. Because my interest is not the journey, my interest is in the final destination. I have to reach at 150 degrees Celsius. I would love to reach as fast as possible. Then there will be time where you will hold the reaction, and जहाँ पे आपका synthesis reaction होगा, that is your target temperature जहाँ पे आप उसे कितने टाइम के लिए होल्ड करते हो. So reaction optimize करने के लिए आप 2 options, either play with your temperature or play with your time. Suppose आपको जैसे आपने पूछा ना कि मेरा रिएक्शन एक, अगर एक जैसे आपने पूछा कि मेरा रिएक्शन एक टेम्परेचर के बाद ज्यादा एक्सपोज करने से मेरा इफेक्ट ज्यादा टेम्परेचर पे एक्सपोज करने से वो कन्वर्ट हो जाएगा. सो आप यहाँ पे टेम्परेचर इंक्रीज नहीं कर सकते, यू हैव लिमिटेशन, देन यू कैन प्ले विद द टाइम, राइट. सो यू हैव टू ऑप्टिमाइज बेस्ड ऑन, अगर आप उसमें हाई टेम्परेचर पे जा सकते हो, यू आर अलाउड टू गो टू द हाई टेम्परेचर, आप टेम्परेचर इंक्रीज कर लीजिए. अदरवाइज अगर आप टेम्परेचर इंक्रीज नहीं कर सकते तो टाइम इंक्रीज कीजिए. तो then heat to temperature in time का भी ऑप्शन है, बट आई डोंट थिंक सो कोई यूज करता है. ओके, बट इसको कोई यूज नहीं करता क्योंकि बेसिकली आपका ये वही हो गया जो हम ओपन वेसल में करते हैं. एक टाइम लेके हम पहुंच रहे हैं वो टारगेट टेम्परेचर पे पहुंचने में, और ये बात
10 मिनट उसको मुझे 240 पहुंचाना.
एडवांटेज क्या है?
फ्लक्स टेम्परेचर अंदर हो रहा है. केमिस्ट्री लाइक वी डू रिफ्लेक्स एक्सपेरिमेंट्स, तो हमारा अंदर प्रेशर भी बन गया है और टेम्परेचर भी पहुंच गया है. तो रिफ्लेक्सिंग में हमें सॉल्वेंट की जरूरत पड़ती है.
बट अगर आप यहाँ करते हो 250-40 डिग्री पे, आप बोल रहे हो 10 मिनट में पहुंचना है, अगर वो 2 मिनट में पहुंचता है तो आपके लिए डिसएडवांटेज क्या है?
जो बायो प्रोडक्ट्स हम स्लो हीटिंग करते हैं तो फिर उनकी स्लो रोस्टिंग होती है, स्लो रोस्ट होती है. और एक अगर हम डायरेक्ट कंटेनर्स पे नहीं रहते तो डिसइंटीग्रेशन.
So depending upon your requirement, आप वो कर सकते हो. Mostly heat as fast as possible ही करते हैं. Then you have this constant power. तो अगर मैं heat as fast as possible करता हूँ, suppose
So I just need to mention the, click on A. I just need to mention the target temperature, at what temperature I want to perform my reaction. And then there is a option of stirring speed set करने का. So 3 steps है, तो तीनों के ऊपर मैं different stirring speed set कर सकता हूँ from 0 to 1200 R. ठीक है? But if I put it into temperature in time, then अगर मैं यहाँ पे जो भी target temperature देता हूँ, then उसके साथ मुझे यहाँ पे इसको time भी देना होगा कि अगर 150 डिग्री पहुंचना है तो कितनी देर लगा के, कितना टाइम लगा के पहुंचना है. So you need to set, suppose like it's in hour, minutes or second. So suppose मैं यहाँ पे 5 minutes लगा के करूँगा. Then we have this third option of constant power. So अगर आप power based programming करना चाहते हो, तो you have to give the temperature as well. ये बेसिकली सेफ्टी के लिए है कि 150 से ऊपर नहीं जाना चाहिए मेरा. एंड दिस इज द पावर जहाँ पे आप 850 वॉट तक पावर सेट कर सकते हो. सो थ्रू आउट योर रिएक्शन इट विल गिव द सेम. जो भी आप करना चाहो, एनी वॉट भी करना चाहो.
डोमेस्टिक वाले पे 10 वॉट नहीं होता है. जब हम डोमेस्टिक में बनाते हैं, एक्सपेरिमेंट करते हैं, तो उसमें 10 वॉट नहीं हो पाता.
So heat as fast as possible is my program. Suppose 150 degree. So ये क्या करेगा, 150 डिग्री पे जाएगा. Then next step is hold time. अब यहाँ पे ये है, this is मेरा my reaction time. मैं यहाँ पे रिएक्शन का टाइम सेट करूँगा कि मुझे 5 मिनट के लिए 150 करना है, 10 मिनट के लिए करना है, 15 मिनट के लिए करना है. So this is your reaction time. Suppose I'm keeping it 10 minutes.
In this case, how will I come to know that जो conventional इसमें 4 to 5 hours का
simple logic.
यहाँ पे 15
Always remember Arrhenius equation. वो यहाँ पे बहुत काम आती है. कि अगर आप कोई रिएक्शन 80 डिग्री पे कर रहे हो या 100 पे कर रहे हो, मान लीजिए 2 घंटे लगा के, आप अगर यहाँ पे 110 सेट कर रहे हो, उसको 1 घंटे कर दो. 120 कर रहे हो, उसको 30 मिनट्स कर दो. सो यू कैन यूज दैट. तो आपको वो बेसिकली एक तरीके से आपको आइडिया हो जाता है कि मुझे अप्रोक्सीमेटली. सो अगर आपका कोई रिएक्शन 5 मिनट में हो रहा है, आप उसे 1-2 मिनट एक्स्ट्रा भी रखोगे तो आई डोंट थिंक कोई इशू होगा. सो आप उस तरीके से ऑप्टिमाइज कर सकते हो. बट एक बेसिक आइडिया हो जाता है कि मैं अगर जब ओपन में मेरा ये 4 घंटे में 6 घंटे में 100 डिग्री पे हो रहा है, तो मुझे कितना करना है. तो आप आर्हेनियस इक्वेशन के अकॉर्डिंगली अपना रिएक्शन इसमें कर सकते हो. देन अगर आपको लगता है कि उसमें कम हो रहा है, ज्यादा है, या जो भी है, आपका रिएक्शन कंप्लीट हुआ है, 90% कंप्लीशन है या जो भी है, आप टेम्परेचर टाइम के साथ उसके बाद दोबारा उसको प्ले कर सकते हैं. बट एक बेसिक आइडिया आपको रिएक्शन को कैसे करना है वो यहाँ से आ जाता है. ठीक है. Then there is the last step is cooling temperature. So you can set the cooling temperature between 30 to 70. इसका रिएक्शन से कोई लेना देना नहीं है. दिस इज ओनली फॉर योर सेफ्टी पर्पस. क्योंकि अगर मैं आपको अलाउ कर दूं कि 200 डिग्री पे आपने एक रिएक्शन किया और आप उसको हाथ में लेके खोल दो, तो इट्स नॉट सेफ फॉर यू. सो दिस इज द टेम्परेचर विच इज सेफ, 70 डिग्री से नीचे का. एंड आप इसको 30, 40, 50, 60, 70 जितना रखना चाहो रख सकते हो. इससे फर्क सिर्फ इतना ही पड़ेगा, अगर आप इसको 70, 65, 60 रखते हो तो आपका कूलिंग थोड़ा जल्दी हो जाएगा. अगर वही आप उसे 30 डिग्री तक करोगे तो वो कूलिंग के 5-7 मिनट एक्स्ट्रा और लग जाएगा, ओपन होगा. सो दैट्स द ओनली डिफरेंस. विल कीप इट एज सपोज 60 डिग्री. देन आप यहाँ से स्टरिंग सेट कर सकते हो. आपको अगर आप सेम रखना चाहो तो सेम रख लीजिए. स्टरिंग स्पीड आपको कैसे सेट करना है, बेसिकली अगर आपका बहुत ज्यादा विस्कस रिएक्शन है तो आप स्टरिंग स्पीड हाई रख दीजिए. अगर आपका मॉडरेट है तो आप 500, 600. और अगर आपको बिल्कुल स्टरिंग करना ही नहीं है तो भी आप उसको कर सकते हो. स्टरिंग से आपको यूनिफॉर्म हीटिंग मिलती है बेसिकली. दैट्स द. तो ये मेरा हो गया. देन आई ओके. So now my test is complete. Program is complete. I'll start. So start होते ही आपका ये कवर बंद होगा ऑटोमेटिकली. देन आपका ग्राफ आपको दिखेगा, वहां पे आपको पूरा दिखता रहेगा कि किस तरीके से आपका रिएक्शन प्रोसीड कर रहा है. ठीक है. देन आपको रिएक्शन प्लान करने का दूसरा एक और है. आपको अगर पिछला कोई कॉपी नहीं करना तो आप यहाँ पे अपना जाइए, जो भी नाम देना है, सपोज दिया, यानी आपको यहाँ से तो आप यहाँ से कोई चूज कर सकते हो. अगर आपने कोई ऑलरेडी मेथड बना के रखा हुआ है वो कर सकते हो। अगर नहीं है तो आप यहाँ से स्टैंडर्ड ले सकते हो कोई भी, देन आप यहाँ पे अपना ऑप्टिमल जो भी आपको रिएक्शन के पैरामीटर्स डालने हैं वो डाल सकते हो। दो तरीके से आपका प्रोग्राम हो जाता है। और यहाँ पे जब आप स्टार्ट करोगे तो आपका ग्राफ आ जाएगा। ठीक है, इंस्ट्रूमेंट के बारे में
तो डाउट हो तो यू कैन आस्क ना।
अगर आपको इंस्ट्रूमेंट ऑपरेशन के बारे में कुछ पूछना है, यू कैन आस्क, क्या करना है, कैसे करना है। अगर इसमें कुछ डाउट है, प्रोग्रामिंग में कुछ डाउट है, तो आप पूछ सकते हो। फाइल कैसे क्लोज ओपन करना है, क्या सेफ्टी है, क्या रखना है।
सो ड्यूरिंग द प्रोसेस हम एडिट इन कर सकते हैं ना, अगर मुझे टेम्परेचर मैंने 105
रिएक्शन चल रहा है, सब
Yes,
कुछ आपको करना है, तो जब आप यहाँ पे टेम्परेचर के ऊपर जब IR आया है, यहाँ पे क्लिक कर दीजिए। वो आप वहाँ पे सपोज आपको लगा 120 पे, आपको लग रहा है कि नहीं मेरा मटेरियल का क्वालिटी खराब हो सकता है, तो आप मैं उसे लोअर टेम्परेचर पे करना या हाई पे करना। तो आप ड्यूरिंग द रिएक्शन एडिटिंग आप टाइम की भी कर सकते हो, आप टेम्परेचर की भी कर सकते हो, एंड आप स्टरिंग चेंज करना चाहो वो भी कर सकते हो ड्यूरिंग द रिएक्शन। बट एवरीथिंग विल बी रिकॉर्डेड। अगर आप चेंज करोगे तो वो स्टेप्स यहाँ पे आ जाएंगे, जो आपकी रिपोर्ट आएगी उसमें भी होगा कि आपने इस पॉइंट ऑफ टाइम ये चेंज किया है, सो एवरीथिंग विल बी रिकॉर्डेड।
ठीक है, चलिए अब हम लोग 10 बजे लोग यहाँ खड़े हो जाए।
हाँ, एक ग्रुप बना रहे हैं इंटरनेट।
कौन एक्सपेरिमेंट किया और नेक्स्ट टाइम इसको बुलाओ। आयशा बेटा आप लोग इधर तो अभी सबसे पहला एक्सपेरिमेंट हम लोग करेंगे, विल मेक अ फ्लोरेसेंट डाई। ठीक है, हाँ, I just need 10 people here so that I can explain it to you properly. Okay, so for fluorescent dye हमको चाहिए होगा resorcinol और हमको चाहिए phthalic anhydride, because it's a Friedel-Crafts reaction, तो हम लोग इसमें जिंक क्लोराइड as a catalyst ऐड करेंगे। Right? Can you write it for me? बस हम लोग क्या कर रहे हैं, बिकॉज हम यहाँ पे सॉल्वेंट फ्री रिएक्शन कर रहे हैं, तो इसलिए हम लोग अपने रिएक्टेंट्स को पहले ही फेस्टिवल वाटर से ग्राइंड कर रहे हैं। सी दैट रिसोर्सिनॉल और थैलिक एसिड दोनों को ग्राइंड कर दिया है। आपको बताया है वायर, ठीक है, वायर इसलिए ले रहे हैं बिकॉज माइक्रोवेव का सबसे बड़ा एडवांटेज क्या है कि हम लोग रिएक्शन को स्मॉल स्केल पर प्लान कर सकते हैं। जब हम लेबोरेटरी में करते हैं तो हम 2 ग्राम 3 ग्राम 1 ग्राम 4 ग्राम ऐसे शुरू करते हैं। यहाँ पर हम जो क्वांटिटी ले रहे हैं दैट इज 0.1 ग्राम 0.02 ग्राम, इतना छोटा छोटा क्वांटिटी ले रहे हैं हम लोग, एंड वी आर गेटिंग परफेक्ट रिजल्ट फॉर दैट। यहाँ पर अभी जो हम मिक्स हो गया सॉर्सिनॉल और थैलिक एनहाइड्राइड हमने ग्राइंड कर दिया बिकॉज वी आर डूइंग इट सॉल्वेंट फ्री, कोई सॉल्वेंट ऐड नहीं करेंगे हम लोग इसमें कैटलिस्ट जरूर ऐड करेंगे। अच्छा ना, जब ये लोग प्रिपेयर कर रहे हैं तब हम लोग यहाँ पर क्या करेंगे, विल गो टू द टास्क लिस्ट। टास्क लिस्ट में आई डू इज, क्योंकि यहाँ पे मैंने बहुत एक्सपेरिमेंट्स कर रखे हैं, मैं कॉपी कर रही हूँ। कॉपी करने के बाद मैं ए पे जाऊंगी और मैं आज इस एक्सपेरिमेंट का नाम दे दूंगी, कुछ अच्छा सा नाम। क्या नाम दिया जाए इस एक्सपेरिमेंट? हैरी पॉटर दे दूं? हैरी पॉटर दे दूं? हैरी पॉटर, ठीक है, हमने नाम को सेव कर लिया। अब हम जाएंगे इसकी रिएक्शन कंडीशन पर। रिएक्शन कंडीशन में जैसा कि अभी सर ने बताया था आपको, हीट एज फास्ट एज पॉसिबल का ऑप्शन ऑटोमेटिकली आ जाएगा, तो उसको हमें कुछ नहीं करना है। हमें क्या करना है, यहाँ पर टेम्परेचर चेंज करना है। तो जितना हमने लिटरेचर पढ़ा है उसके हिसाब से इसका टेम्परेचर होना चाहिए 146। ठीक है, हम यहाँ पे फिर ओके कर देते हैं। अब हम जाएंगे टाइम। टाइम हमने 10 मिनट का रखा है, इसको थोड़ा सा कम कर देते हैं, इसको हम कर देते हैं 7 मिनट्स। उसके बाद रोटेशन का कोई फर्क नहीं पड़ता है इसमें। बेसिकली हमें टेम्परेचर सेट करना है और टाइम सेट करना है। बिकॉज हम लोग उसमें मैग्नेट नहीं डाल रहे हैं, तो आरपीएम से कोई लेना देना नहीं है, हमारा एक्सपेरिमेंट इसमें भी हो जाएगा। अब हमको करना क्या है, इसको यहाँ पर, अच्छा यहाँ पे G10 वायल मैंने ऑलरेडी सिलेक्ट किया हुआ है, पर जब आप लोग फर्स्ट टाइम प्लान करेंगे तो यहाँ आपको करना पड़ेगा सिलेक्ट। तो हम इसको ओके कर देते हैं। इज द वायल रेडी बेटा? G10 जो वायल है उसको हमें इसमें ही रखना है। हाँ, so we put this thing inside. अब इसका जो सेप्टम है, जो G10 का वायल का सेप्टम है, वो थोड़ा सा बंद करने में ट्रिकी है। उसको हमें एक पर्टिकुलर एंगल पे स्लाइड करके फिर दूसरे हाथ से बंद करना पड़ता है, तो वो भी आपको बंद करके ठीक है। आप ठीक है, इसमें नहीं जिंक वो डाल दिया, जिंक क्लोराइड डाल दिया, बस स्पैचुला से डाल दो जिंक क्लोराइड। आ गया जिंक क्लोराइड, ये और ले लेना जस्ट अ ड्रॉप। हाँ, एक कैटलिस्ट में एक ड्रॉप ही यूज हो रहा है, हो गया। अच्छा, आप बता दीजिए ये सेप्टम को कैसे बंद किया जाएगा। इधर आ जाओ, एक सेकंड, आप बता दीजिए। दिस इज योर ड्रिपिंग वायर, इसको कैसे बंद किया जाएगा ये थोड़ा सा ट्रिकी है, मुझे भी नहीं आता।
पहले हम एक जगह प्लेस करेंगे उसको कि वो नीचे पैक,
एक तरफ से उसे पैक रखना है आपने। हाँ, आवाज आई? जब ये आवाज आएगी तब ये सील हो गया है। नाउ यू कैन लुक एट द रिएक्शन मिक्सचर हियर। ये सॉलिड है, कलरलेस है, हम बना रहे हैं डाई। सो लेट अस सी व्हाट हैपेंस नाउ। आई एम प्लेसिंग इट इनसाइड द माइक्रोवेव। प्रोफेशनली यू कैन शो इट इनसाइड माइक्रोवेव पे। हमने वायल को रख दिया है और उसके बाद हम स्टार्ट दबा रहे हैं। जैसे ही मैंने स्टार्ट दबाया, वो ऊपर का जो बटन है वो ऑटोमेटिकली बंद हो गया। इट्स अ स्विवन स्लाइड बटन, वो ऑटोमेटिकली बंद हो गया है। अब आप लोग देख सकते हो, यहाँ पे दिखा दो। अब रिएक्शन जो है वो अपनी स्टार्ट हो जाएगी, हो जाए स्टार्टिंग ये यहाँ से आना शुरू। ओके, अब यहाँ पर देखो ये ग्राफ आना शुरू हो गया है। कैन यू सी, छोटा सा ग्राफ आना शुरू हो गया है, 3 लाइंस आ रही है इसमें। सो इसमें पहला टाइम, पहला है 140 डिग्री टेम्परेचर को रीच करना। जब वो रीच कर जाएगा तो ये वाली लाइन मेरी रेड हो जाएगी। रीच करने के बाद वो 10 मिनट उस मेरे वाइल को टेम्परेचर 140 डिग्री देता रहेगा फॉर 10 मिनट्स। मैंने 8 मिनट सेट किया है, सो इट विल कीप ऑन गिविंग दिस टेम्परेचर। और उसके बाद कूलिंग टेम्परेचर है हमारा 60 डिग्री सेल्सियस। ठीक है, तो अब हमारे पास 5-6 मिनट का टाइम है, सो वी कैन डिस्कस एनीथिंग, वी कैन आस्क क्वेश्चंस। ओके, अच्छा, जब ये एक्सपेरिमेंट हम लेबोरेटरी में करते हैं तो डू द सेम प्रोसेस बट विद मोर अमाउंट ऑफ रिएक्टेंट्स एंड इट टेक्स अप्रोक्सीमेटली 50 मिनट्स टू 1 आवर। कभी बनाया है फ्लोरेसेंट? बनाया है? तो उसमें क्या करते हैं, आप लोग राउंड वाटर फ्लास्क में सारी चीजें मिक्स करके मैग्नेटिक एक्सटेरर पे रख देते हैं, 1 घंटा रखते हैं, है ना, और उसके बाद उसको खत्म करते हैं। तो यहाँ पे देखिएगा, जब आप 7 मिनट के बाद हम इसको वायल को निकालेंगे तो उसके बाद आप देखिएगा कि आपको रिएक्शन वायल में ही ऑरेंज क्रिस्टल्स, स्लाइटली ऑरेंज एंड ब्राउन क्रिस्टल्स मिल जाएंगे। फिर हम उसका टेस्ट करके दिखा देंगे। मेरा टेम्परेचर पहुंच चुका है 140 डिग्री पर, बिकॉज ये देखो ग्रीन लाइन आ गई, पहले ये रेड थी जब टेम्परेचर जा रहा था, तब ये now I have reached that temperature of 140 डिग्री। अब मेरा सेकंड प्रोसेस स्टार्ट हो गया। 8 मिनट तक मेरी वायल को 140 डिग्री का टेम्परेचर मिलता है। दैट वाज सेकंड प्रोसेस। यू हैव टू वेट। यहाँ पे हमको टाइम इलैप्स दिख रहा है, 1 मिनट 29 सेकंड्स हो गया है, बाकी का टाइम बचा हुआ है। ये देखो 149 डिग्री पहुंच गया। मैंने कितना सेट किया था? 140। तो ये क्या करेगा, ये अपने आप उसको कम करना शुरू कर देगा। और जब 140 पर पहुंच जाएगा तब रुक जाएगा। चार 5 मिनट के बैक में जाओ, जस्ट 5 मिनट्स तक, 5 मिनट में एक्सपेरिमेंट कंप्लीट करें। ये टमाटर वो डिस्कस है, आपको क्लास में डिस्कस करनी है। एनईपी वाले आप लोग कौन से? सेकंड हाफ ये रेड वाली लाइन दिख रही है, इसका मतलब मेरा रिएक्शन हो रहा है। और कब तक कंप्लीट होगा? जब तक ये रेड वाली लाइन यहाँ तक नहीं पहुंचेगी। तुम नहीं उसके अंदर आप ये सब्जेक्ट पढ़ना हाँ वो अच्छा 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 यार अब मेरा हो गया इससे मैंने कर स्टॉप कर दिया। बातें कर सकते हैं लोग सब। कोई और क्वेश्चन है आप लोगों का बच्चों? बेटा कुछ क्वेश्चन है आप लोगों का अबाउट माइक्रोवेव? हाँ लव रिएक्शन तो चल रही है, so 2-3 मिनट तक यू हैव एनी डाउट्स? मुझे बहुत सारी फोटो ली थी मैंने, अच्छी लगी। एक बाई 1 लाख वाइल का प्राइस, 1 वाइल 1 लाख। इंस्ट्रूमेंट अब आप इसका अप्रॉक्सीमेटली 30 लाख। ओके गाइस स्माइल। वो बात हेलो गाइस, यहाँ पे हमारे वर्कशॉप चल रहे हैं। लॉगिन कर दूं मैं थोड़ा प्लीज? ले ले भाई उसकी। जिसको आवाज नहीं क्वेश्चन है अब मैम ने बोला था 0.1 उसका क्या है थोड़ा सा बस वो वाइफ क्योंकि मैम एक डाउट है कि अपन ने 0.1 ग्राम और 0.2 ग्राम क्वांटिटी में लिया तो वो तो काफी सारा था, तो कुछ 0.1 ग्राम तक हम स्केल डाउन कर सकते हैं। ये हमने कितनी क्वांटिटी में लिया? ज्यादा लिया था 0.75 ग्राम से स्टार्ट कर सकते हैं। और वो वाइल तो हाफ फिल्ड से थोड़ा कम ही होना चाहिए ना जो। हाँ हमने जिंक क्लोराइड कितना लिया? 0.03। अभी जो हमारे बाकी के एक्सपेरिमेंट्स हैं उसमें भी बहुत कम कैलकुलेट करके रखा हमने 1.5 ग्राम से स्टार्ट किया तो 0.5 से स्टार्ट कर सकते हैं, लेकिन उस डॉक्यूमेंट्री कैलकुलेशंस रेशियो हर चीज उसी रेशियो के लिए
गार्डियन लेवियोसा ओपन नहीं हुआ। मैम ने कहा था ना हैरी पॉटर तो उसी का वो कर रही है। मैंने तो आपको लास्ट में पूछा था, मैं उनको बता रही हूँ नहीं बोला था। पता है हमको चला कल आ जाना। ये नहीं आ रही, इसको बोला ना आए। आ जाए ये कल आएगी तो क्लास वर्ड लेकर रेडी आयशा इंशा
कंप्रेशन काउंटर है
नहीं, इसमें 0 मार्क्स दिखा रहा था।
लास्ट
जो प्रेशर बार है ना यहाँ से दिख रहा है आपको।
अपने आप
या तो मैं टेम्परेचर कमांड कर सकती हूँ या मैं प्रेशर कमांड कर सकती हूँ। मैं टेम्परेचर बेस्ड एक्सपेरिमेंट से तो प्रेशर को अपने आप से जैसे इसमें कितना ज्यादा होगा तो यहाँ से देखिए क्या
एक बार में हमारा फिक्स रहता है, जैसे हम 10 डिग्री टेम्परेचर पर आते हैं, 10 मिनट्स में फिर हम दोबारा आज पेपर स्टार्ट। एक बार में सारा डाटा सारा हमने एक बार सेट किया 10 मिनट ऐसे करके वो
एक टेम्परेचर फाइनल सेट कर सकते हैं। इसमें आप ये नहीं कर सकते कि पहले 10 मिनट 100 हो जाए, फिर 10 मिनट 200 हो जाए, फिर ऐसे नहीं हो सकता। जो आपका फाइनल टेम्परेचर है आप वही इसमें सेट कर सकते हैं।
कन्वेंशनली रिएक्शन रेट्स निकालते हैं, पहले 10 मिनट के लिए वेट किया, फिर हमने प्रेशर
वो फर्स्ट ऑर्डर तो अंदर जो है वो एयर जो है उससे हमारा वाइट उसके बाद रिएक्शन कंप्लीट हो जाती है। यहाँ से ये चला जाता है आपको देख रहे हैं ना, इससे आप कंप्रेशन आएगी और टेम्परेचर सेकंड की लाइन इसका तो हमने 10 मिनट कर और 3 लाइन और अभी तो फिर रेड लाइट ऐसे हो जाएंगे तब आपको दिख जाएगा। Video. It is asking me कि मैं next file insert करना चाहती हूँ या नहीं, तो अभी मैं नहीं चाहती, अभी मैं इसको cancel कर, अब मैं क्या करती हूँ? Yes. Orange. यहाँ पे directly you are getting the fluorescence. आप जरा एक बार चीज देखते हैं, उसमें can you open the इस तरह Can you see the color?
Yes, ma'am.
Sense. Yes. Can you see that? Starting materials there. क्या है?
Halogen hydride.
Starting materials में हमारे colorless है. डाई जो बनी हुई orange color की, और उसके बाद this is the application. Yellow, green, fluorescent. Right? बता दिया. Anything else? चलो अब आप क्या ना नेक्स्ट बैच या कि सारे के सारे आ गए एक्सपेरिमेंट अपने हाथ से करती हूँ यस मैम आई विल नॉट लेट यू होल्ड अ वायर बट
1 lakh.
नेक्स्ट एक्सपेरिमेंट तुमने पढ़ा होगा बैकमैन रीअरेंजमेंट बच्चे लोगों ने पढ़ा होगा
Thank you so much.
बैकमैन रीअरेंजमेंट के लिए ऑक्सिम बनाते हैं ऑक्सिम के लिए हम लोग बेंजोफिनॉल और हाइड्रोक्सिलामीन हाइड्रोक्लोराइड तो वो हमने यहाँ पे स्टोक्योमेट्रिक में पे करके रखा हुआ है कैन यू आयशा कौन से वाले हाँ बट आई कांट लेट देम हैंडल द वायर व्हाई आयशा रुको आयशा रुको बाकी काम हम
वायु वाला
एक्चुअली सारा स्टोक्योमेट्रिक आयशा
Yes, ma'am.
बहुत सारी चीजें में कर दो
ये तो मुझे वायु तो
कोई और बच्चे चेक करें
Yes, ma'am.
कुछ बच्चे रिएक्शन फाइल सेट कर रहे हैं कुछ बच्चे यहाँ पे एक्सपेरिमेंट सेट कर रहे हैं ठीक है सबसे पहले टास्क लिस्ट सिलेक्टेड है और ठीक से कॉपी आप इसको डी को दबाओ ठीक से आप बताओ क्या रखेंगे सारे कशिश चलो कशिश नाम अच्छे से कशिश के साथ हम बेंजोफिनोल भी लिखते हैं क्योंकि कशिश के नाम से याद रहेगा
मैम रीजनल कॉलेज है कॉलेज का नाम है
कशिश ऑक्सीडेट
पैक करता है इधर ऑक्सीजन डाल
एक्स कैपिलरी आई ओके कर देते हैं इसको ये आपने कशिश ऑक्सीजन आ गया अब ये मेरे रिएक्शन पैरामीटर्स फ्लोरेसेंट वाली डाई तो मैं इसमें अपने रिएक्शन पैरामीटर सेट कर देती हूँ यहाँ से प्रेस कर 3 डॉट्स को देखो हीट एज फास्ट एज पॉसिबल टेम्परेचर है इसका 90 डिग्री 5 मिनट्स। हीट एज फास्ट एज पॉसिबल को अपने को कुछ नहीं करना। आप टेम्परेचर पे जाओगे, मेरा टेम्परेचर इसको लिखो 90 डिग्री। ठीक है, ओके करो। अब जहाँ पर होल्ड टाइम कितना लिखा हुआ है? 5 मिनट्स। 5 मिनट्स। अच्छा, अब कैपिलरी ट्यूब है, कैपिलरी ट्यूब से हो जाए, मॉइस्चर है उसमें कंपाउंड। किसी और चीज से देखो ना, प्रॉपर से करना तो यहाँ तक आएगा। प्रॉपर तो नहीं है, ये ग्लास रॉड डाल के देखो जाएगी। सारा पकड़ डालेगा तो कैपिलरी ट्यूब तो नीचे से ऊपर आ रही है। हाँ, इस ट्राई करना, इसको ओके प्रेस करके ये पार्ट ओके कर दो। हमारा एक्सपेरिमेंट सेट ये G10 यहाँ पे सेलेक्ट हम चेक कर लेंगे। Heat as fast as possible. 5 minutes. Solvent free, solvent minimum 40. 1 to 2. इसको ओके कर देते हैं। अब हमको वाइल सेट इसको डाल दिया। वाइल ये सेट बना रही है। डाल दो थोड़ा सा। सुनो आयशा, 2 ml नीचे कम डाल। इसमें रखा इतना उस वाले बना से उठा। हाँ, मैशिंग से ये रखा मुझे। नॉक्सिन करा दी और एक बेंजोक्विनोन नॉक्सिन करा दी। जल्दी करने वाली, जल्दी खत्म हो जाएगा। हाँ, 5 मिनट में और खराब हो तैयारी तो और नहीं करेंगे। बहुत आ गया पेमेंट आ गया। चल अब आप इसको सील कर दीजिए। सबसे एक तरफ से
हो गया हो गया हो गया।
ऊपर से कर सकते हो। हाँ, इसके अंदर डन। अब हम क्या करेंगे, यहाँ से स्टार्ट दबा देंगे। दबा दिया। यहाँ पे हम एक बार चेक कर लेते हैं कि जो हमने पैरामीटर्स दिए थे वही लिखे हुए हैं क्या। क्या लिखा है पहले 90 डिग्री। नेक्स्ट लाइन में क्या लिखा है, नेक्स्ट लाइन में क्या लिखा है 60 डिग्री। ठीक है, एक्चुअली अब मैं ना कूलिंग में एडिट एक्सपेरिमेंट कर लेती हूँ क्योंकि मेरे को कूलिंग चाहिए। एडिट के लिए पहले स्टॉप करना नहीं, कुछ स्टार्ट हो गया। अब हो जाएगा। मैं कूलिंग टेम्परेचर जो है ना, हाँ कूलिंग टेम्परेचर को मैं 45, ठीक है ओके फिर से ओके कर देते हैं। हो गया एक्सपेरिमेंट। वहां पे सेट चेंज आ गया। क्या लिखा है यहाँ पे 45। ठीक है, तो मैंने मिड एक्सपेरिमेंट अपना एक छोटा सा डेटा चेंज कर दिया। अब हम लोग 5 मिनट वेट करेंगे। ये सारे ग्राफ्स देख रहे हो, यहाँ पे ये ग्रीन लाइन मतलब पहुंच गया, टेम्परेचर 90 डिग्री पहुंच गया। नॉट इवन 1 मिनट, शायद मेरे ख्याल से 15 सेकेंड में वो 90 डिग्री पहुंच गया। अब इट विल मेंटेन दिस टेम्परेचर फॉर 5 मिनट्स। 5 मिनट वेट करेंगे, उसके बाद हम ये कूलिंग हो जाएगी। फिर ऑक्सिम में क्या करते हैं, अंदर जो रिएक्शन हुई है उसको हम आइस कोल्ड वाटर में डाल देते हैं। जैसे ही डालते हैं हमको ऑक्सिम सॉलिड प्रेसिपिटेट होके आ जाता है। ओके, तो ज्यादातर अब मैंने तो बेंजोफिनोन लिया है, तुम बेंजोफिनोन का कोई सा भी वेरिएंट ले सकते हो, पर हमें नहीं पता कि वो रिएक्शन होगी कि नहीं होगी। तो हम लार्ज स्केल पे करके क्या करेंगे, तो हम इसमें प्लान कर, फिर अगर रिएक्शन हो जाती है बढ़िया, वी कैन प्लान इट ऑन अ लार्जर स्केल। तो इस तरीके से कोई भी रिएक्टेंट लेकर हम लोग रिएक्शन प्लान कर सकते हैं, स्टोक्योमेट्री मेंटेन करके। वाइल शुड नॉट बी मोर देन हाफ सॉल्वेंट फ्री। पिछला वाला एक्सपेरिमेंट सॉल्वेंट फ्री था, ये वाले एक्सपेरिमेंट में मैंने मिनिमम सॉल्वेंट यूज किया है। जब हम एक्सपेरिमेंट करते हैं लैब में तो हम 50 ml इथेनॉल लेते हैं और 35 ml पानी लेते हैं, तो कितना सारा सॉल्वेंट लेते हैं। यहाँ मैंने कितना लिया, 3 ml, दैट इज ऑल, और रिएक्शन हो जाएगी और रिएक्शन की यील्ड भी बहुत अच्छी आ जाएगी। वहां जो मैंने लिए रखे हुए ना वायल्स, उसमें देखो ऑक्सीजन की यील्ड, मेरे बच्चे का हाँ उसमें, वेयर आर माय स्टूडेंट्स, उस्मा, आयशा, 1/4 तो वो फ्लोरेसेंट डाई है, उसमें कितना ऑक्सीजन हो। बेटा देखो दिखाओ ना एक्सपेरिमेंट, ऑक्सीजन वाला दिखा दो कहाँ है। कितनी सारी यील्ड आई थी, और हमारा स्टार्टिंग में तुमको बताती हूँ कितना लिया है हमने। बेंजोफिनॉन हमने लिया है 0.36 ग्राम, 0.36 ग्राम, जबकि जब हम लेबोरेटरी में करते हैं तो 3.6 ग्राम लेते हैं, ठीक है। और उससे भी वो यील्ड देखो, हाँ बेंजोफिनॉन ऑक्सीजन यील्ड देखो कितनी सारी आई है। इसी तरीके से, अच्छा आप मुझे आइस कोल्ड वाटर चाहिए और ग्लास स्टरर चाहिए।
5 ml
ठीक है, मैं डाला, 5 नंबर लिखा है, मैं डाला मैंने 3 है। देखिए हमें, हमारा माइक्रोवेव का पर्पस क्या है, एनवायरनमेंट का कम से कम सस्टेनेबल, सॉल्वेंट कम यूज करेंगे, आपने 1 घंटे की गैस बचा ली। बेटा यहाँ रखो, यहाँ रखो, और एक ग्लास वाटर दे दो। ओपन द वायर, एक घंटे को तुम इधर आ जाओ या उष्मा को भेज दो, वायर ओपन कर देंगे, फिर इसको पकड़ा देना। लेट अस गो फॉर रिएक्शन। वायर तुम ओपन कर दो या आयशा ओपन कर देगी, फिर इनको पकड़ा देना, ठीक है। आ गया ना, अच्छा सा, कितना अच्छा। हाँ हाँ लेना ना, उसकी ले ली थी वायर की, येलो क्रिस्टल्स की।
पावर है और
वो जैसे डिफरेंट कलर में डिफरेंट पैरामीटर्स को रिप्रेजेंट कर रहे
पहले वाला ग्राफ तुम्हारा
हैं वो वाले जो स्क्रीन पे
येलो और
यहाँ मार्क्स है, वो भी वही है,
वो भी वही है ना,
हाँ येलो टेम्परेचर।
पैरामीटर्स को ही दिखा रहा
हाँ हाँ वही दिखा रहे हैं।
देखो ये प्रेशर वाला ग्रीन है ना, या ग्रीन येलो टेम्परेचर का है। यहाँ जो एरो का कलर है वही वो ग्राफ की लाइन का।
हाँ 3 मिनट निकल गए, यहाँ पे भी टाइम देख सकते हो, 3 मिनट 54 सेकेंड्स निकल गए, 1 मिनट बाकी है, उसमें देख लेते हैं अभी क्या होता है। अच्छा
वो खुद डिसाइड करते
है। टाइम का हम लोग खुद से डिसाइड करते हैं कि इतना टाइम
टाइम हम डिसाइड करते हैं आर्हेनियस इक्वेशन से। अगर आपने टेम्परेचर बढ़ा दिया तो टाइम आधा कर दो, है ना, वो इक्वेशन यही कहते हैं कि डबल द टेम्परेचर, increase the temperature to 10 degree and the reaction will double side। आप अगर थोड़ा सा टेम्परेचर बढ़ाते हैं तो टाइम उसके हिसाब से कम कर दीजिए। फिर इसमें भी हिट एंड ट्रायल होता है, हमने टाइम कम करके देखा बड़ी अच्छी 70% यील्ड आ गई, फिर हमने और कम करके देखा 90% यील्ड आ गई, और कम करके देखा इम्प्योरिटी इतनी आ गई। ये भी होता है, इम्प्योरिटी आ गई, साइड प्रोडक्ट्स बन गए, जैसे एल्डोल कंडेंसेशन हम करते हैं तो उसमें साइड प्रोडक्ट्स बन जाते हैं बहुत सारे। तो हिट एंड ट्रायल इसमें भी है, लेकिन बहुत ही स्मॉल लेवल पर। योर एक्सपेरिमेंट इज ओवर नाउ, अब वो कूलिंग स्टार्ट करेगा, कूलिंग के लिए वो प्रेशर देगा, ठंडी हवा देगा। रश्मि मैम को दिखाएंगे, रश्मि मैम आएंगे ना, उनको दिखा दो एक बार, फ्लोरेसेंट डाई दिखा दो।
एक का कितना मिनिमम टेम्परेचर है?
लोग कहते हैं कि हमें 40 से नीचे नहीं जाना चाहिए, कभी कभी कहते हैं रूम टेम्परेचर तो लेकिन सर्दी में 20 डिग्री भी चला जाता है, उस पर मना करते हैं, कहते हैं 40 डिग्री तक आप हैंडल कर सकते हो, फाइल हैंडल कर सकते हैं 40 डिग्री। अभी ये रेड वाला कूलिंग स्टार्ट हो गया है, करेगी तो सिर्फ खोल के दे देना, आपको पोर करते हुए ग्लास रॉड से स्टर करना है, जब आप स्टर करोगे तो सॉलिड प्रेसिपिटेट अपने आप आता जाएगा और आपको ऐसा लगेगा कि उसमें तो ऑलरेडी सॉलिड है, दैट सॉलिड इज रिएक्टेड सॉलिड, आपस में उनकी रिएक्शन हो चुकी है। वो हम कैसे पता करते हैं, जब हम इसमें डालते हैं, इसको फिल्टर करते हैं और इसका मेल्टिंग पॉइंट लेते हैं, तो मेल्टिंग पॉइंट हमें रिएक्टेंट्स का नहीं मिलता है, हमें प्रोडक्ट का मिलता है। Okay, so the process is same. What we are reducing is only the reaction time. अच्छा, तो आप स्टेज पे बुलाऊंगे तो 2-3 लाइन बोलना वर्कशॉप के बारे में, क्या ठीक है? सबको दिखा दिया, मीना मैम को दिखा दिया, अगर ये आज का रिजल्ट भी तो दिखाना चाहिए, 3 बार से तो अपने आ ही रहे। मैंने मेंशन किया था, अगर मैं मेंशन ये देखो ये ग्रीन लाइन, इसका मतलब कूलिंग खत्म हो गई, अब ये खुल जाएगा। कैंसिल कैंसिल ये जो 2 रिएक्टेंट आपने डाले थे वो आपस में मिक्स करके प्रोडक्ट बना चले, ओके, इसको पानी में डालेंगे तो हमारा ऑक्सीजन प्रेसिपिटेट होगा। आपको इसमें डालना है, अच्छा स्टार्ट डालते जाओ, यस ये देखो आ गया, ठंडा है ना, पीने का नहीं होता, ठंडाई वाली है। अच्छा और वो तो बाई प्रोडक्ट है, उसको छोड़ दो, इसमें रख दो, फाइल इसमें रख दो। सी दिस इज ऑक्सीजन, जितना आपको रिएक्टेंट दिख रहा था उससे कहीं ज्यादा है ये, ठीक है, तो हम ये नहीं सोच सकते कि जो हमारा वायल में था वो तो सॉलिड था, प्रोडक्ट ये वो तो रिएक्शन हो गई, फाइन, कितना सारा प्रोडक्ट आया है, इसको अभी हम थोड़ी देर और शेक करेंगे और फिल्टर करेंगे तो विल गेट लॉट ऑफ प्रोडक्ट, जबकि हमने बहुत ही कम क्वांटिटी यूज की थी, फाइन, ठीक है, हैप्पी, चले वैलिडिटी के लिए चलते हैं, अब हो गया।
भी रख देती हूँ कल यूज।
हाँ लेकिन सुबह आके सबसे पहले से चार्ज पे लगाना है
कैसे लगा भाई?
साई राम। चलो नहीं नहीं
लगा ठीक है।
वाई
Good evening, everyone. It is my pleasure to stand before you today for the valedictory function of our one-day workshop on unlocking the power of Monowave Microwave Reactor. Today has been a very special and useful day for all of us. Through this workshop, we learned about the Monowave Microwave Reactor, which is an advanced equipment which saves energy and helps chemists speed up reactions and works in a more environment-friendly way. We got to see how this reactor makes chemical reaction faster and safer compared to traditional methods, which is very exciting for students like us. I am happy to share that this workshop was conducted in a hybrid mode, where some students joined us online and some came here in the campus. On behalf of all the students, I, Aisha Siddiqui, sincerely thank our respected director, Dr. Pratibha Singh Madam, our principal, Dr. Archana Srivastav Madam, head of department, Dr. Neena Arora Madam, all the faculty members, our resource person, and everyone who worked hard to organize this workshop. I also thank all the participants for their active participation and making this workshop a successful one. Now, I would like to invite our head of department, Dr. Neena Arora Madam, to please come and present the workshop report.
Good evening once again. In this last session of today's workshop, Honorable Vice Principal Dr. Renu Mishra, our speaker Shri Vikesh Chauhan ji, Shri Praveen Srivastav ji, faculty members from different colleges, research scholars, students, and all the participants who joined us online. As we are in the process of concluding the session, this workshop, Unlocking the Potential of Monowave Microwave Reactor. It is now near the end. Workshop began with the inaugural session. Chief guest was Dr. Vivek Katare ji, Executive Director, MP Council of Science and Technology, Bhopal. Chief guest highlighted shared with us the different applications of microwave radiations in different fields. He highlighted the chemistry is the central science and we must follow green practices in every field. Director Dr. Pratibha Singh Madam conveyed her blessings and highlighted the importance of sustainable. Technical session was focused on green chemistry principles and how this microwave radiations work in the process of synthesis. This was conducted by Dr. Anita Dutt Konar, Assistant Professor, UGC Assistant Professor, Rajiv Gandhi Pradyogiki Vishwavidyalaya. She also gave different examples of the chemical reactions which can be conducted with the use of this microwave reactor. In this session, Mr. Vikesh Chauhan, Regional Sales Manager, Anton Parr, described about the basics of the microwave reactor. He explained how this microwave works, what are the different features, how different models are available for the synthesis and how sophisticated way this microwave reactor works. Then in the technical session 3, demonstration on the microwave reactor was given by Mr. Vikesh Chauhan, Regional Sales Manager, Anton. He described on the instrument the working process of the working process of the microwave reactor. All the participants actively participated in this session, and their query was sorted by Mr. Chauhan very nicely. After this, Dr. Varsha Saxena conducted the experiments with the students and demonstrated the different reactions performed on the Monowave Microwave Reactor. I hope everyone enjoyed this workshop and these different technical sessions. And I think we have successfully achieved our objective of the workshop, which was to create the awareness, to sensitize the students, researchers about the importance of green chemistry. And I hope that after going from here, you will think before doing anything. What you are synthesizing, you will think what is the what waste we are generating, what chemicals we are using, how sustainable this reaction is, what we are doing. Is it sustainable? This kind of thought should be in your mind always, whatever you are doing. Then this workshop will be successful. I request all of you to please think before doing anything, because we have to take step for the protection of our Mother Earth. We have only one planet, and it is the responsibility of each one of us to save this Mother Earth. Every action, our action, is responsible for whatever will be our future. So think logically before doing whatever you do. So I request once again all of you to follow the green practices for the sustainable future. So thank you so much, everyone, for your cooperation, your support, and hoping the same in the future also. Thank you so much.
Thank you so much, ma'am. Now, I would like to invite Dr. Rashmi Sharma, Madam, Associate Professor RIE, to please come and give her valuable feedback about this workshop.
Esteemed Vice Principal Madam of this very institute, Shri Sathya College for Women, Dr. Renuka Ma'am, the Vikas Chauhanji, who is representing the Anton Park, and the colleague, another colleague from the Anton Park, a program coordinator and the IQSC coordinator of this institute, Dr. Neena Arora Ma'am, faculty members of the Department of Chemistry from this institute and from other institutes, those are present here attending this workshop. Dear students, research scholars, very good evening to each one of you. On behalf of me, and I'm representing Regional Institute of Education, Bhopal. So I'm bringing the best wishes from the institute for each one of you here. Good evening, everyone. This workshop has been really very fruitful today. I would like to convey my heartfelt congratulations to the coordinator, to the institute, to this very college, the Sathya College for Women, for organizing such workshop, which is indeed a need of the hour. Today, we talk about so much about the sustainability. We talk about the environment, but what really we are doing here? That is a big question with all of us. And as the academicians, as teacher and students, what is our contribution? So this very workshop is one step towards that sustainability, which we are quite oftenly talked, but actually not worked on. So by having this very workshop on the use of monowave microwave, we are promoting the green synthesis, green practices, those are really environmental friendly. In one of the session, we have again reminded about the 12 principles of green chemistry. Those principles, although we all are aware of, but how to incorporate these very important principles of green chemistry into our day-to-day classroom practices, into our day-to-day research practices, that is the main crux. And by attending this very workshop, we also have learned one important aspect about the green synthesis. So my congratulations to the organizers. And at the same time, I would like to mention that this collaboration between the academia, the students, scholars of chemistry, and of this institution should go in a long way. This is not the end. This is just the initiation. This is just a starting point for this collaboration. And personally, I, being the faculty of RI Bhopal, would like to collaborate here as a department of chemistry from the RI Bhopal with this Sathya Institute, so that we can have many more such collaborations. And I would like to mention another important aspect from this platform, since I belong to NCERT. At NCERT, at RI Bhopal, we are also trying to promote the green practices, the discipline-specific green practices. And in that very order, we do have the microscale chemistry laboratory designed and developed by NCERT. With the help of this microscale green chemistry laboratory, we are promoting the chemistry experiment, not only in chemistry, that microscale kits have been developed for biology, for mathematics, for physics, and for at different stages, for the middle school stages, for the high secondary, and the secondary stages. And the same kit is being used for the experiment at the undergraduate level also, the some of the experiments, not all, with the help of those kits. So that is also one of our initiative, one of the NCERT's initiative, which we are doing with the help of that microchemistry laboratory kit. I would like to invite each one of you to our institute anytime when you have time, or we may design something of such nature, so that we invite you all to be part of that workshop or that exposure of that kit also, because that also is one of the initiative where we are trying to reduce the pollution at this source itself. And in the morning session also, we have discussed about this point, that the chemistry laboratory are the ultimate source of the pollution. It's the soil pollution and is the water pollution. So whatever the drainage comes out from the chemistry laboratory, if we have this study, in fact, we have done in our institute, in the surrounding of the chemistry laboratory, all the nutrients, the microbes, they all have gone, and the land becomes barren. And wherever that drainage goes in the water bodies, the water also contaminated, that also is polluted. So why don't we start the reducing the pollution from the source itself? And this very workshop is, again, I feel, is the one in step in that direction only. So once again, I would like to convey my heartfelt thanks to the organizers, to the institute, which is Shri Sathya College for Women, and to all the participants. Those have been thought about this, and they are contributing from their small steps towards the more greener and more cleaner world. And that's what the need of the hour. So once again, my congratulations to each one of you, and thank you very much. This has been really very fruitful day for all of us. Thank you.
Thank you so much, ma'am. Now, I would like to invite a few participants for their valuable feedback.
Good evening, everyone. Myself, Prashasti Shukla, and I am grateful for the opportunity to share my feedback on today's workshop. As a student, I found the workshop really well organized and engaging, with a nice balance between theory and practical demonstration. The hands-on session with the Monowave Microwave Reactor made it much easier for me to grasp its application in organic synthesis. I especially appreciated how it connected to green chemistry approaches in a very practical way. It actually inspired me to think about microwave assisted synthesis in my future research work. Overall, it was a very enriching and insightful experience that broadened my understanding of advanced lab instrumentation. Thank you, everyone.
Thank you, ma'am. Now, I would like to invite Ms. Supriya Singh, madam, to please come up on the stage and present the vote of thanks.
Thank you, Aisha. Sairam, on behalf of the Department of Chemistry, I would like to express heartfelt gratitude to our esteemed speaker, Mr. Vikesh Chauhan, Regional Manager North, Antonpar, and his colleague, Mr. Praveen, Regional Manager Bhopal. I extend my sincere thanks to our Vice Principal, Dr. Renu Mishra ma'am, respected faculty members, research scholars, and students. A big thank you to our technical staff, supporting staff, and everyone who worked tirelessly to make this program a success. Lastly, I would like to acknowledge students whose dedication played a significant role in its success. Their names are Vaishali, Aisha, Uzma, Dipali, Prashasti, Lakshmi, Ananya, and Trisha. Thank you all for patience hearing. Thank you.
All the participants who joined
Yes.
online.
Thank you all the participants who joined online and offline. Thank you so very much. Ma'am, anything else you would like to say?
Thank you so much, everyone.